Welcome back to Sleep Nova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. We speak of everything, yet we hardly grasp its magnitude. Everything is the totality of existence, the stars and galaxies, time and space, energy and matter, life and mind. It is all that is, all that ever was, all that ever will be. In its embrace are the quiet dust under our feet and the shining furnaces of distant suns, the hum of a thought and the roar of a supernova. To contemplate everything at once is to stand at the shore of an infinite ocean, awed and humbled. Even our most fleeting reflection on the cosmos can send a shiver down the spine, as if some deep part of us remembers that we are a part of this grand tapestry, woven into its very fabric. On a clear night, under a vault of stars, we gaze upward and attempt to fathom our place in a vastness without obvious bounds. We see pinpoints of light scattered across a canvas of darkness, each a sun, perhaps with its own planets and stories. We feel small, yet we are connected to all of it. The iron in our blood, the calcium in our bones, the carbon in our DNA, these were forged in the hearts of ancient stars. We are children of the cosmos, built of its matter, energized by its light, and guided by our curiosity to understand it. Through science and imagination, we stretch our minds toward the edges of the universe, seeking to grasp how all of this came to be. From time immemorial, we have gazed at the heavens and spun stories about our place among the stars. Today, our tools are telescopes and equations, but the sense of wonder remains as profound as ever. In this journey, we will blend science and poetry, fact and metaphor, as we explore the cosmos on every scale. We will touch on cosmology and physics, astronomy and mathematics, philosophy and human curiosity, all the lenses through which we seek understanding. Together, let us venture to the very beginning of time and back, and to the farthest reaches of space, in pursuit of the story of everything. Our journey begins at the very beginning, at the origin of everything we know. In the primordial darkness, before a single star had ever shone, all that would become the universe was cradled in a point smaller than an atom. It is nearly impossible to imagine. A seed of unimaginable density and heat. A single point that held the potential for galaxies, for life, for every atom and every moment in time. And then, in an instant about 13.8 billion years ago, that seed exploded into growth. There was a flash of pure creation, a moment we call the Big Bang. Time and space themselves were born in that moment. What had been nowhere became everywhere. What had been nothing became everything. The newborn universe expanded with incomprehensible fury. In a tiny fraction of a second, it swelled from microscopic to cosmic scales. This extraordinary growth spurt, known as cosmic inflation, stretched space like a balloon inflating at faster than light speed. Distances between points grew by an enormous factor, smoothing out any clumps or curves. Inflation explains why the universe today is so uniform and flat on large scales. It was as if any initial wrinkles in space were ironed out by this tremendous expansion. A smooth, seething fireball emerged from that initial burst. Tiny quantum fluctuations, random little flickers of density in that early vacuum, were blown up by inflation into slight variations in the otherwise even spread of matter. These faint imprints would one day guide the formation of galaxies, but for the moment, the infant universe was a hot, dense soup of energy. As inflation settled, the energy driving it transformed into matter and light. The universe was 1 second old. In that first second, space was filled with an intense, blinding glow, radiation so hot that it would have vaporized anything, though as yet, there was nothing but fundamental particles. Matter and energy were not yet distinct. They flowed together in a plasma, a fluid of raw creation. Protons and neutrons jostled in temperatures of billions of degrees. In the minutes that followed, the entire universe itself became a nuclear reactor. These building blocks began to combine in countless tiny nuclear forges across the young cosmos. Protons fused with protons, neutrons linked with protons. By 5 minutes of cosmic time, the first atomic nuclei had formed. The simplest elements came into being: hydrogen, the lightest of all, and helium, its slightly heavier kin. A trace of lithium also appeared. In that brief early epoch of nucleosynthesis, the universe forged the basic chemical foundation it would use to build everything else. About 3/4 became hydrogen and 1/4 helium by mass, an elemental newborn universe. Still, no atoms as we know them could yet exist. The universe was far too hot for electrons to settle into orbits around nuclei. Instead, electrons careened freely through the dense plasma, scattering light incessantly. Photons, the particles of light, were trapped in a cosmic fog, bouncing from one free electron to another. Space glowed as bright as the interior of a star, but no light could travel far. The universe was opaque, a brilliant radiance suffused within a swirling, glowing mist. As seconds turned to minutes, minutes to hours, and hours to years, the young cosmos continued to swell and cool. Hundreds of thousands of years passed. Expansion took its toll on the fireball, diluting and cooling it steadily. At around 380,000 years after the Big Bang, a critical threshold was crossed. The temperature fell enough that electrons could finally be captured by nuclei. Protons clutched electrons to form hydrogen atoms. Helium nuclei gathered electrons to become helium gas. This transition is called recombination, though it was the first time such combination had occurred. With electrons now bound into atoms, the fog lifted. The once captive light was free at last. In every direction, a brilliant afterglow burst forth and raced away through space. The universe that had been opaque became transparent. That first light still surrounds us today. It has cooled to a gentle microwave glow that bathes the entire sky. The cosmic microwave background, the oldest light we can see. Back then, it was a searing, orange-white illumination everywhere. As space expanded and cooled, that light's wavelength stretched beyond red, through infrared, and into the microwave part of the spectrum we detect today. Discovered as a faint hiss in radio antennas, this afterglow is a whisper from the time the universe took its first breath as a transparent cosmos. The universe then entered a deep, dark age. With the primal light released and streaming onward, space itself went dark. There were not yet any new sources of light. The primordial gases, mostly hydrogen and helium, now drifted through expanding space like a vast, invisible fog. Gravity, the great sculptor, began to gently tug on the ever-so-slight variations in density left by inflation. Regions that were just a bit denser than average exerted a stronger pull, drawing in matter from their surroundings. Invisible threads of gravity started weaving patterns in the darkness. Over tens of millions of years, those threads pulled gas into clumps. The silent clouds grew denser and tighter until, at last, there was fire again. Perhaps 100 million years after the Big Bang, the first stars were born. Deep in massive collapsing clouds of hydrogen and helium, the pressure and heat ignited nuclear fusion. Starlight pierced the darkness. These first stars were giants, short-lived behemoths burning hot and blue, forging heavier elements in their cores as they shone. They lived for only a few million years before dying in titanic supernova explosions, seeding the surrounding space with the new elements they had cooked up: carbon, oxygen, nitrogen, iron. Ingredients that one day would be essential for planets and life. The death of each star sent enrichment into space, and out of the ashes, new generations of stars would eventually form. Their brilliant ultraviolet light also gradually burned off the primordial hydrogen fog in intergalactic space, reionizing the cosmos and allowing light to travel freely everywhere. With the birth of stars, the cosmos had begun to light up structure by structure, ending the long night of the Dark Ages. The cosmic dawn gave way to a growing day as the first stars and nascent galaxies illuminated the heavens. As stars gathered, they formed the first proto-galaxies, small galactic building blocks that later merged into larger ones. Gravity continued its tireless work on grander scales. Stars bound themselves into galaxies, and galaxies gravitated into clusters. Over hundreds of millions, and then billions of years, a vast cosmic web took shape. Galaxies pulled on one another along filaments of invisible matter, collecting into chains and sheets. Imagine a spider's web made not of silk but of galaxies, strung along invisible filaments, with enormous voids of near-empty space in between. Astronomers mapping millions of galaxies, for instance in the Sloan Digital Sky Survey, have unveiled this vast cosmic web in detail, huge filaments like the Sloan Great Wall stretching across hundreds of millions of light-years, and immense voids nearly empty of galaxies. It serves as the large-scale structure of the universe. Galaxies grouped like sparkling dew on cosmic threads, clusters at their intersections, and between them, great dark gaps where few galaxies shine. Interestingly, researchers have even drawn analogies between the cosmic web and biological systems. One experiment showed that a slime mold, when presented with simulated galaxy clusters as nutrient sources, grew tendrils that closely traced the filaments of the cosmic web, as if nature repeats patterns on vastly different scales. From a vantage point far away, the universe would look foamy or spongy, matter gathered into fibrous clusters surrounding empty cavities. And within each galaxy, countless stars swirled, orbiting their galactic centers like bees around a hive. What about the universe as a whole? Is it shaped like a sphere, a saddle, a donut, or an infinite flat expanse? As far as we can discern, space on the largest scales is remarkably flat, like an endless plane. If you set off in a straight line among the galaxies, you would not curve back around to where you started, at least not within any distance we can observe. The cosmos could extend forever, infinite in extent. It might also be finite yet unbounded, curving back on itself only on scales beyond our observational reach, rather like the surface of a balloon is finite, yet has no edge. Current measurements of cosmic geometry show no significant curvature. To the best of our knowledge, parallel beams of light travel straight and never meet. It is currently unknown whether the universe might eventually loop back in some topologically complex way, like a 3D torus. But if it does so on a scale far larger than the observable horizon. In all directions, space stretches out similarly, giving us no hint of an edge or a boundary. We are, however, limited in what we can see, not by any solid wall at the universe's edge, but by time itself. The observable universe is a sphere around us, about 46 billion light-years in radius, delineated by the distance light has been able to travel since the Big Bang. We can only see as far as the light that has had time to reach us. Beyond that horizon, light from those regions has not yet arrived, and perhaps never will. Thus, we gaze out at a bubble of the universe around us. Beyond it, the mystery continues, perhaps with more galaxies and more cosmic web stretching indefinitely, or perhaps something radically different. For now, it remains hidden, a tantalizing unknown just out of reach. The cosmic horizon is not only a physical limit, it's also a reminder of our cosmic myopia. It's like standing on the shore of a vast ocean at night. We see the dark waters meet the sky at the horizon and wonder what lies beyond. Our cosmic horizon is such a shore, and though we cannot see past it, we imagine an endless sea beyond. Even as structures formed and stars lit up, the overall expansion of space never halted. The universe kept stretching, carrying galaxies farther apart from each other. The very fabric of space is like an ever-expanding canvas,
and the galaxies are like dots of paint on that canvas, drifting away as the canvas grows. The light that travels between galaxies is stretched too. As space expands, wavelengths of light elongate, shifting toward the red end of the spectrum. Thus, when we observe distant galaxies, their light is reddened, a cosmological redshift that encodes their motion through the expanding space. In the early 20th century, astronomers armed with new telescopes made a profound discovery. Nearly all galaxies beyond our local group are racing away from us, and the farther they are, the faster they recede. Edwin Hubble measured this relationship, finding that the speed of recession is proportional to distance. Today, this rate of expansion, known as the Hubble constant, is roughly 70 kilometers per second per megaparsec, meaning a galaxy about 3.3 million light-years away recedes at roughly 70 kilometers, and one twice as far at about 140 kilometers. This linear relationship, now called Hubble's law, was revolutionary evidence that the universe is expanding uniformly in all directions. It is not that we are at the center of an explosion, but rather that space itself is swelling, so every galaxy sees others moving away. Imagine raisins in a rising loaf of bread. Each raisin sees the others receding as the dough between them expands. Just so, our Milky Way and all galaxies are like raisins embedded in the expanding space of the cosmos. Yet even as Hubble and others revealed an expanding universe, other observations soon uncovered a deeper mystery in those galaxies. In the later 20th century, astronomers like Vera Rubin noticed that stars at the outskirts of spiral galaxies were orbiting their galactic centers at startling speeds, too fast to be explained by the gravity of the visible stars and gas alone. According to Newtonian physics, those outer stars should have been flung off into space, or conversely, one would need far more mass in the galaxy to hold them in their orbits. Something unseen, some additional gravitating mass, was providing the extra pull. Similarly, clusters of galaxies were found to contain far more gravity than the visible matter could supply. It was as if an invisible halo of mass surrounded clusters and individual galaxies alike. This mystery substance was dubbed dark matter. It does not shine or interact with light, making it invisible and detectable only through its gravity. But it is abundant, far more abundant than the ordinary matter we see. Roughly 85% of the matter in the universe is dark matter, about 5 times more mass than in normal atoms. It acts as the scaffolding of the cosmic web. It clumps under gravity, forming massive halos, and ordinary gas falls into those halos to form galaxies. Without dark matter's guiding hand, the universe would lack much of the structure we observe. Galaxies might not have had enough gravitational glue to coalesce as they did. We even observe gravitational lensing, light from distant objects bending around invisible mass, revealing dark matter's presence. In colliding galaxy clusters like the Bullet cluster, the normal matter, hot gas visible in X-rays, can be seen to separate from where most of the gravity is. The gravitational center follows the unseen dark matter, providing direct evidence of this hidden mass. We still do not know what dark matter is. Perhaps some as yet undiscovered elementary particle that interacts only weakly with normal matter, often hypothesized as WIMPs or axions, or something more exotic like primordial black holes or a modification of gravity itself. Experiments deep underground and in particle accelerators are attempting to detect dark matter particles directly, so far without success. For now, we infer dark matter's presence by how it holds galaxies together and how it tugs on light passing by. It is the universe's invisible skeleton, a shadowy scaffolding that shaped the beautiful pattern of galaxies and clusters, all while remaining hidden from our eyes. As if dark matter were not mysterious enough, an even stranger ingredient dominates even that. For a long time, scientists assumed that the expansion of the universe, while continuing, should be slowing down over time. After all, gravity pulls all matter together. The collective gravity of galaxies, dark matter, gas, and stars should gradually tug at the expansion, perhaps even causing it to reverse in the far future. But in 1998, two teams of astronomers observing distant Type Ia supernovae, exploding stars used as standard candles, made a shocking discovery. The supernovae were dimmer and farther away than expected, indicating that the expansion of the universe was not slowing at all. It was speeding up. Over the last few billion years, the galaxies have been accelerating away from each other. Some kind of force or energy inherent to space is pushing them apart. Decades earlier, Albert Einstein had introduced a cosmological constant into his equations of general relativity to allow for a static universe, not realizing the universe actually expands. When Hubble's expansion came to light, Einstein reportedly called that constant his greatest blunder. But now, the accelerating cosmos implies something like Einstein's constant truly exists after all. We call this phenomenon dark energy, a name that signifies how little we truly understand it. Dark energy appears to be a property of space itself. Every cubic centimeter of vacuum seems to carry a minuscule amount of energy that, summed over billions of light years of emptiness, dominates the universe. Today, roughly 68% of the universe's total energy content is this dark energy, with about 27% dark matter and only 5% normal matter composing the rest. It behaves almost like an anti-gravity, driving galaxies apart on large scales and overpowering the attractive force of gravity at cosmological distances. Perhaps dark energy is a fixed property of the vacuum, a realization of Einstein's cosmological constant, or perhaps it changes over time, a dynamic field dubbed quintessence. Upcoming observatories and surveys are dedicated to measuring the expansion history more precisely, in hopes of discerning the true nature of this mysterious energy. For now, dark energy remains an enigma at the heart of cosmology, a gentle but inexorable push woven into the fabric of space-time. What does an accelerating expansion mean for the future? The fate of the universe hinges on dark energy's nature. If dark energy remains constant, a steady push that continues indefinitely, then the expansion will not only continue, but accelerate forever. Galaxies that are not gravitationally bound to us will recede faster and faster, eventually zooming away at such speeds that their light can no longer reach us. In tens of billions of years, distant galaxies will disappear beyond our horizon, leaving only the gravity-bound local group of galaxies, by then likely merged into one large galaxy, visible. If we look far, we'll see darkness where once galaxies twinkled. Over extremely long timescales, the stars within our remaining galaxy, or merged Milk-Dromedar galaxy, will age and die. New stars will form more slowly as the available gas becomes sparse. Trillions of years from now, the last stars will exhaust their fuel and flicker out one by one, leaving a universe populated only by faint stellar remnants, white dwarfs cooling to black, neutron stars, and black holes. The cosmos will grow colder and darker as eons pass. Eventually, even black holes will evaporate via Hawking radiation, on timescales so vast, 100 years or more, that they defy imagination. What remains will be a thin haze of fundamental particles and energy, spread so dilute that for any given volume of space, on average, there might be essentially nothing in it. This is the Big Freeze or heat death scenario, a universe that expands forever while cooling asymptotically toward absolute zero, approaching a state of maximum entropy where no organized energy remains to do work. If an astronomer were alive in that far future of a Big Freeze, they would see a very different sky. Beyond our small gravitational neighborhood, no galaxies would be visible at all, only an endless black void punctuated by the occasional faint glow of a red dwarf or the spark of a distant supernova, becoming rarer with time. The evidence of the Big Bang itself would fade. The cosmic microwave background, which today is a cool 2.7 K glow, would be stretched to radio waves so long and weak as to be undetectable, The chemical elements would slowly transmute as protons perhaps decay over immensely long times, if proton decay is a real phenomenon. Eventually, it would be a universe of scattered particles and low-energy photons, drifting in an ever-growing silent darkness. Time would continue, but virtually nothing of interest would happen. It is a state as close to true cosmic stillness as can be. The universe would have effectively died, not with a bang, but with a long, drawn-out whimper. There are even more violent speculative possibilities. If dark energy is not constant but instead grows stronger with time, imagine a form of phantom energy, then the acceleration would steepen catastrophically in the far future. In such a scenario, the repulsive effect of dark energy could increase without bound. One could imagine the final moments of such a universe. Galaxies rush away from each other at ever-increasing speeds. Eventually, in the distant future, the expansion's pull becomes so strong that it overcomes the gravity holding galaxies together. First, galaxy clusters are pried apart. Later, the galaxies themselves begin to fly apart as their stars disperse into the expanding void. Then solar systems destabilize, planets drift away from their stars. As the end approaches, even stars and planets themselves would be torn apart, and then molecules and atoms. In the last fractions of a second, the tidal forces of expansion would become essentially infinite, shredding the very subatomic particles. This hypothetical final calamity is called the Big Rip. It would be a universe ending in a kind of ever-accelerating explosion, where every bond, gravitational, electromagnetic, even nuclear, is overcome by the expansion of space. One moment, you might have galaxies. Moments later, only individual atoms. Finally, nothing at all but a thin, featureless energy as space rips itself apart. It's a highly speculative scenario. Current data do not favor such extreme dark energy behavior, but it serves to illustrate the dramatic ways our universe's story could conclude under different rules. On the other hand, what if dark energy were to weaken over time, or even reverse sign? Or what if the universe had contained so much matter that gravity could eventually overwhelm expansion? In those cases, the expansion might slow down, stop, and ultimately reverse. Distant galaxies that are now receding would one day halt and begin to come closer again. This is the Big Crunch scenario, the opposite of the Big Bang. In a universe headed for a big crunch, observers in the far future might see the expansion first slow to a crawl. Distant galaxies that once sped away would linger at the edge of visibility. Then, gradually, they would start to approach, their light shifting from red back to blue. The cosmos would begin to shrink. Over billions of years, separated clusters of galaxies would converge. Previously unreachable galaxies would become visible again as they rush inward. The cosmic microwave background temperature, which had been dropping, would begin to rise as the universe contracts and heats up. Eventually, the night sky would no longer be dark, but aglow, first dotted with an increasing number of bright galaxies coming together, then suffused with the glow of a background fire as intergalactic gas is compressed and reheated. In the final epoch, the entire sky might blaze like the surface of a star, white hot, as galaxies merge into a single, incandescent mass. Finally, all matter and energy would crash together in an ultra-dense state, perhaps a mirror image of the Big Bang. Some have imagined that such a collapse could bounce, an implosion leading to a new explosion, a Big Bang after the Big Crunch, giving birth to a new universe. This Big Bounce idea suggests a cyclic cosmos without beginning or end, eternally reborn. However, given what we observe, particularly the presence of dark energy, a Big Crunch seems very unlikely for our universe. The balance of evidence indicates that we are headed toward eternal expansion, either the Big Freeze or Big Rip, with Big Freeze considered far more plausible under current data. Nevertheless, thinking about these scenarios reminds us that our universe's story might have multiple chapters, and perhaps even an epilogue beyond our own cosmos. As we ponder the fate and origin of our universe, we naturally wonder, is our universe the only one, Or is it just one bubble in a vast, frothing sea of universes? Modern theories in cosmology and physics have opened the door to the idea of a multiverse, the possibility that our universe is not alone, but part of a far larger system of universes. The existence of dark energy and the precise balance of physical constants in our universe have led some to wonder if our cosmos is just one of many, its properties one random draw among myriad universes. In a multiverse, what we call fine-tuned constants of nature, like the strength of gravity or the charge of the electron, might vary from one universe to another. We find ourselves in one that permits galaxies and life simply because those that don't would be sterile and uninhabited, with no observers to notice them. One compelling multiverse idea arises from the theory of eternal inflation, a variant of the inflationary scenario we discussed earlier. In eternal inflation, the rapid expansion of space didn't end everywhere at once. While inflation stopped in our region, allowing particles and galaxies to form, other regions of space might still be inflating, or might have ended their inflation at different times, each giving rise to its own bubble universe. Our universe, then, would be one such bubble among countless others, expanding within a larger inflating space-time. Each bubble could have its own distinct laws or constants. Some might be barren, with no matter or with physics hostile to complexity. Others might be roughly similar to ours. Perhaps others are wildly different with more dimensions or different fundamental forces. We cannot directly see these other bubble universes because they would lie beyond our cosmic horizon and indeed beyond any space-time connection with us. But they are a natural extrapolation of inflation theory. These other universes could be as real as our own, each constituting its own reality bubble. The multiverse concept comes in different flavors. The Level 1 multiverse essentially says that if space is infinite and uniformly filled with matter, then far beyond our observable horizon, there could be regions identical to ours, or slightly different or vastly different, simply by random chance arrangements of matter. In an infinite universe, every possible configuration of particles, every possible history, would occur somewhere. Our observable universe would be just one patch of an infinitely vast quilt. The Level 2 multiverse corresponds to the eternal inflation scenario, bubble universes. Each bubble might have different physical constants or particle types, because the process of symmetry breaking in physics could end up differently in each one. One bubble might have a stronger electromagnetic force. Another might have a neutron a bit heavier, preventing stars from working. We find ourselves in a bubble that is congenial to complexity because only such bubbles can produce observers. Another intriguing idea is the Level 3 multiverse, which arises from quantum mechanics, the many worlds interpretation. In quantum theory, every event that has multiple possible outcomes, like a particle decaying or not decaying, is sometimes thought of as splitting reality into multiple branches. According to this interpretation, all possible outcomes actually occur, each in its own branch of the wave function of the universe. So in one quantum branch, universe, the cat is alive. In another, it is dead, to invoke the famous Schrödinger's cat thought experiment. These parallel universes are usually thought to be non-communicating, existing in a superposed mathematical state, rather than separate inflating bubbles. But some argue they are just as real as our own. In effect, this would mean that with every quantum event, the universe, at least at the level of quantum information, splits into multiple histories, creating an ever-branching tree of parallel realities. If true, the number of universes would be mind-bogglingly large and constantly increasing. There is even a conjectured Level 4 multiverse, the ultimate ensemble, which posits that all universes that can be described by consistent mathematical structures exist in some sense. In this view, mathematics and reality are one and the same. Any self-consistent set of physical laws, any mathematical model, corresponds to an actual universe somewhere. This is a philosophical speculation more than a scientific theory, but it underscores how far the multiverse idea can be taken. So, could it be that what we call everything, our observable cosmos, is but a drop in a much grander ocean of existence? It's possible. At present, the multiverse remains a theoretical idea. We have no direct evidence of other universes, and some argue we never could, by definition. Yet the concept finds footing in serious science because it can arise naturally from models like inflation, and because it offers answers to questions like why our universe has the properties it does. They might be random picks from a larger distribution. If the multiverse is real, then the totality of existence is even grander than the universe we've been discussing. It means there could be countless other Big Bangs, countless other expansions, perhaps countless other versions of you and me, or perhaps realities utterly without analogy to anything we know. It is a speculative, almost metaphysical extension of our theories, one that reminds us that as vast as the universe is, there could be more, much more, beyond it. No matter how many universes exist, we know that we can only directly explore our own, and it has plenty of mystery to keep us occupied. One such mystery is deeply connected to our everyday experience, the nature of time. Time flows ever forward, carrying us from moment to moment. We remember the past and anticipate the future, but we never experience events in reverse. This one-way direction of time, from past to future, is called the arrow of time. Why does time have an arrow? The answer, as far as physics can tell, lies in entropy. Entropy is a measure of disorder or randomness. The second law of thermodynamics states that in an isolated system, entropy tends to increase or, at best, stay the same. It never decreases spontaneously. This law gives a direction to processes. Things go from ordered to disordered, not the other way around. An egg breaks and scrambles, but a scrambled egg does not unbreak itself into a whole egg. A drop of ink disperses in water, but the ink won't gather back into a concentrated drop on its own. These processes are not forbidden by any fundamental microscopic law. Newton's and Schrödinger's equations work the same forward and backward in time, but they are overwhelmingly unlikely to happen in reverse, because that would require a decrease in entropy. The arrow of time in our universe is fundamentally linked to the initial conditions of the cosmos. The universe began in an extraordinarily low entropy state. This might sound strange because the early universe was a hot, dense plasma which seems very disordered, but in fact, it was extremely uniform and simple, free of complex structures, making its entropy lower than it could have been. It's as if all the matter and energy were evenly spread out and gravitationally unclustered, a very ordered configuration compared to what could be. Because the universe started with such low entropy, there was essentially nowhere to go but toward higher entropy. As the universe expanded and cooled, entropy increased, gradients smoothed out, structures formed even as overall disorder grew. For example, the formation of stars and galaxies increases local order, but overall entropy still rises due to the production of lots of waste heat and the gravitational settling that releases energy. The arrow of time is a manifestation of this rise of entropy. We perceive time flowing forward because that is the direction of increasing entropy. If you were to film a glass shattering and play it backwards, you'd see entropy decreasing and immediately intuit that time is reversed in the film. In the real universe, we do not see such things. One might ask, why was the entropy of the early universe so low to begin with? This remains one of the deep, unanswered questions in cosmology. Some suggest it might be a boundary condition of our universe, perhaps set by a prior state or by the laws of quantum gravity. Others propose that if there are multiple universes or cycles, we naturally find ourselves in one that started in a low entropy state, because only such a universe can develop the complexity needed for observers. Regardless, that low entropy beginning is what allowed an arrow of time to emerge. From it flowed the entire history of structure and complexity. Stars shine, increasing entropy by radiating heat. Life grows and metabolizes, increasing entropy in surroundings even as it creates local order. And eventually stars die and things run down. If we project trillions upon trillions of years forward, in the heat-death scenario, entropy will near a maximum. The arrow of time will effectively fade, not because time has reversed, but because almost nothing changes anymore. There are no organized processes left to distinguish a forward direction. In the far, far future of a big freeze, the universe might reach a state of near equilibrium where, without gradients or differences, the concept of before and after loses much of its meaning. Time and entropy tie together the grand cosmic and the intimate personal. The increase of entropy sets the thermodynamic arrow that makes memory possible. We remember lower entropy past states. It is why we grow older and not younger. It's the reason we can't unmix cream from coffee or unburn a piece of paper. It's fascinating that this everyday irreversibility is rooted in the initial conditions of the entire universe. We've journeyed from the enormous clusters of galaxies to the minute atoms and particles, but we haven't yet delved into the truly fundamental fabric underlying reality, the quantum realm. On the smallest scales, the world behaves in ways that defy our classical intuitions. In the quantum realm, particles are also waves, and everything is described by a fuzzy haze of probabilities rather than definite certainties. Take an electron. In an atom or in transit, it doesn't have a single precise location. Rather, it exists as a cloud of probability, a smeared-out wave of potential positions. Only when we interact with it, measure it, does the electron seem to choose a location or state. This is the bizarre phenomenon of wave function collapse, in interpretations where collapse is a thing. Before observation, Schrödinger's cat is both alive and dead in a quantum sense. Before measurement, the electron has many possible positions. For example, if we shoot electrons at a screen through two narrow slits, something astonishing happens. The electrons, one by one, form an interference pattern on the detection screen, alternating bands as if they were waves that passed through both slits and interfered with themselves. This happens even if we fire them one at a time. It's as though each electron goes through both slits as a spread-out wave. However, if we set up a detector to observe which slit the electron actually goes through, trying to catch it in the act and force it to be a particle going through one path, the interference pattern disappears. Now the electrons behave like little bullets, going through one slit or the other, and no interference fringes form, just two piles behind the slits. The mere act of observation changes the outcome at the quantum level. It's as if nature allows the electron to explore many possibilities, wave behavior, until we insist on knowing which one happened, at which point nature chooses and the wave of possibility collapses into a single result. Empty space itself is not truly empty in the quantum sense. Even in a perfect vacuum, quantum fields are continuously fluctuating. Particle-antiparticle pairs momentarily pop into existence and then annihilate so quickly and so spontaneously that we can barely infer their presence. They leave subtle effects on energy levels and forces. These quantum fluctuations are not just theoretical quirks, they had cosmic consequences. During inflation, those tiny fluctuations in density and energy were stretched out to macroscopic scales. Regions that were ever so slightly more dense or less dense than others became the seeds for all large-scale structure. The spots in the cosmic microwave background that are a bit warmer or cooler, denser or less dense, trace back to these quantum wiggles. It is a breathtaking linkage. The reason galaxies exist where they do is partly because of random subatomic jitter in the universe's earliest moments. The entire cosmic web is essentially amplified quantum noise. Quantum physics underpins nearly everything in our daily experience, even though we don't notice its strangeness on large scales. The atoms in our bodies are held together by electron wave functions and quantum bonds. The sun shines because quantum tunneling allows protons to overcome their electrostatic repulsion and fuse into helium. Without quantum tunneling, the sun's core wouldn't ignite as easily. Computers and modern technology rely on quantum mechanics, semiconductors, lasers. In a sense, the solidity of a rock, the behavior of a chemical reaction, the colors of the rainbow, all trace back to quantum rules. We live in a quantum universe, though its oddness becomes apparent only when we look at small scales or specific conditions. There is also the deep mystery of quantum measurement and reality. Does the wave function collapse when observed? Does the universe split into branches for each outcome? The many worlds idea. No one knows for sure which interpretation of quantum mechanics is correct, or if there's a deeper theory that will resolve these questions. What we do know is that quantum mechanics is astoundingly successful in predicting outcomes. It has been tested to high precision. Reality, at its foundation, is governed by probability waves and uncertainty. It's almost as if nature, at a fundamental level, decides events by a kind of controlled randomness within strict statistical rules. Our voyage has taken us from the beginning of time to the structure of space, from the largest assemblies of galaxies to the subatomic flickers of the vacuum. Along the way, we encountered phenomena that are poetic in their grandeur and scientific in their detail. An afterglow from creation itself still shining to us, invisible matter holding galaxies in its gravitational embrace, a mysterious energy pulling the cosmos apart, and quantum whispers setting the stage for galaxies. Let's return for a moment to that ancient light we freed at recombination, the cosmic microwave background, CMB. After traveling for 13.8 billion years, it reaches Earth as a faint, cold glow in all directions, a few photons per cubic centimeter. In 1965, two engineers, Arno Penzias and Robert Wilson, were using a big horn antenna in New Jersey, trying to eliminate all sources of noise from their radio measurements. They kept encountering a persistent hiss, uniform across the sky, day and night. At first, they thought it might be due to urban interference, or pigeon droppings in their antenna, or instrument malfunction. But none of those explained it. Meanwhile, a group of physicists at Princeton, Dicker, Peebles, et al., had been looking for exactly such a signal. The predicted relic radiation from the hot early universe, which years earlier, scientists like George Gamow had calculated should by now be just a few degrees above absolute zero. Penzias and Wilson had stumbled upon the very signal that those theorists were seeking. It was soon confirmed that this microwave hiss came from all directions uniformly and had a blackbody spectrum of about 2.7 Kelvin, just what the Big Bang model predicted. The cosmic microwave background was the long-predicted afterglow from the hot young universe, now cooled to a whisper. When we map the CMB across the sky, as satellites like COBE in 1989, WMAP in the 2000s, and Planck in 2013 have done with increasing precision, we find it is almost the same in every direction, extremely uniform to about 1 part in 100,000. It's as if the entire sky were painted with one color of incredible smoothness, with only the faintest speckles. Those speckles, the tiny temperature anisotropies, carry a wealth of information. They are the imprints of the primordial sound waves and density ripples in the early universe. The pattern of spots tells us the universe's age, composition, and geometry. By carefully analyzing the CMB, scientists have confirmed the age of the universe, how 13.8 billion years, determined that space is flat to within a tiny margin of error, and measured the ratios of normal matter, dark matter, and dark energy that we mentioned. The CMB is like a baby picture of the universe, taken when it was only 380,000 years old. In that baby picture, we can already see the slight non-uniformities that eventually grew into clusters of galaxies. It's astonishing that we can observe this. When you tune an old television between channels and see static, a small fraction of that static is actually CMB photons. literally relics from the Big Bang hitting your TV's antenna. The CMB also provides evidence that ties together many threads of our story. It confirms the Big Bang. A static universe would not have such a background. It supports inflation. The uniformity and specific patterns match inflationary predictions. And it informs the dark matter models. The CMB pattern is sensitive to the amount of invisible mass. It is a Rosetta Stone for cosmology, decoded through careful, rigorous science. And yet, when one simply gazes at the visualizations of the CMB, with its gentle swirls of red and blue indicating tiny temperature fluctuations, one can't help but feel a sense of wonder. This mottled oval image, often shown in textbooks and documentaries, is the imprint of the primordial cosmos on the sky, the oldest light we will ever see, a light that has traveled for almost the entire history of the universe to reach us. Within this vast cosmic unfolding, on at least one small planet, the expansion and cooling of the universe eventually led to something new: life and consciousness. The atoms forged in stars and scattered by supernovae became the raw material for new star systems. About 4.6 billion years ago, one particular cloud of gas and dust, already enriched by previous generations of stars, collapsed to form our Sun and its family of planets. The third planet from this sun had the right conditions for a remarkable chemistry. In its early oceans and coastal environments, a rich molecular broth swirled. On this young Earth, a complex chemistry brewed in warm ponds, in tidal pools, and around underwater hydrothermal vents. Complex molecules formed in the warm, wet cradles, perhaps sparked by lightning in the atmosphere or by geothermal energy in the crust. Perhaps in sunlit shallow pools, left to evaporate on volcanic shores, or in the mineral-rich hot springs on the ocean floor. Simple chemistry crossed the threshold to self-replication. At some point, simple self-copying molecules emerged. This was the origin of life, around 4 billion years ago. From those humble beginnings of primitive microbes, life evolved in complexity and diversity, shaped by mutation, competition, and time. Tiny cells coalesced into more complex cells, which eventually formed multicellular colonies. By around 540 million years ago, the Cambrian explosion filled the seas with an astonishing variety of creatures. Life took hold on land. Plants and fungi colonized the continents, followed by insects and amphibians, then reptiles and dinosaurs. Each living organism was, and is, a little chemical machine, drawing energy from the environment to maintain its internal order, a local reversal of entropy paid for by increasing entropy in its surroundings. In this way, life is a kind of cosmic rebellion against the trend toward disorder, though only a temporary and localized one. Through life, the universe explored an entirely new realm of complexity. After dinosaurs were wiped out 66 million years ago by an asteroid and other factors, mammals rose to prominence. Some primates in Africa, a few million years ago, left the trees for the savanna. They grew bipedal and clever. They made tools and learned to cooperate in groups. By about 300,000 years ago, anatomically modern humans had appeared. With the emergence of Homo sapiens, the universe began to be aware of itself in an unprecedented way. We gazed at the stars with curiosity and imagination. Over thousands of years, we developed language, culture, mythologies about the cosmos. We harnessed fire, energy for entropy consumption. We built shelters. We eventually tilled fields and founded cities. We looked up and saw patterns in the sky, crafting constellations and calendars. Human curiosity pushed us to ask not just how to survive, but why we are here, what the stars are, what the sun is, and how it all began. Fast forward to the modern era. In just the past few centuries, we have, through the scientific method, unraveled many cosmic mysteries. We discovered that those points of light in the night sky are other suns, and some of those suns host planets of their own. We've confirmed thousands of exoplanets and infer that the galaxy holds billions more. We found that our sun is just one star among hundreds of billions in the spiral galaxy we call the Milky Way, and that our galaxy is just one of trillions in the observable universe. We've begun to understand the forces and particles that govern nature. We've peered back in time with powerful telescopes to see galaxies in their infancy, and we've peered into the atom to unlock the secrets of quantum physics. Life, at least here, evolved to consciousness that can contemplate the universe. That is a profoundly poetic fact. We are made of dead stars, and those very ashes have somehow become alive and able to wonder about their origins. The universe spent billions of years evolving us, and through our eyes, it now sees itself. We are a way for the cosmos to know itself, Carl Sagan famously said, encapsulating this truth. Our self-awareness makes the universe not only a physical phenomenon, but also an experience. Through our literature, art, and science, the cosmos has gained the ability to reflect upon itself, to study its own laws, to admire its own beauty. Are we alone in this astounding capability? Perhaps not. The universe is so vast that it seems improbable that Earth would be the only cradle of life. Perhaps in some warm pond on an exoplanet under a distant sun, chemistry has given rise to biology. Perhaps on a moon orbiting a gas giant, beneath an icy crust, alien microbes flourish near thermal vents. Maybe on some planet in the habitable zone of another galaxy, intelligent creatures build their own tools and look up at their sky with questions. As of now, we don't have evidence of life beyond Earth, but the possibility stirs our imagination. Whether life is common or exceedingly rare, the fact remains that life here has transformed a part of the cosmos into something self-aware. And so here we find ourselves, clever, self-aware creatures built of cosmic dust, living on a minor planet, orbiting an ordinary star in a typical galaxy, yet able to contemplate the entirety of existence. Our physical insignificance is undeniable. We are infinitesimal compared to the breadth of the cosmos. Our entire world is just a tiny mote of dust in a cosmic ocean, a pale blue dot adrift among countless stars. But our ability to understand and appreciate the cosmos gives us a significance of a different kind. We might be rare, perhaps the only intelligent beings for parsecs around, or maybe one of only a few in our galaxy. Maybe life teems in the universe, or maybe it is exceedingly scarce. Either way, in our corner of space and time, we are the only known eyes and minds observing the grand cosmic drama. Through us, the universe has become aware of itself. Through our scientific instruments, the universe maps its own structure. Through our poetry and art, the universe speaks of its own majesty. There is something profoundly meaningful about this, even if one views it in a purely secular, scientific way. The cosmos has given rise to beings who can know the cosmos. We have inherited the fiery hearts of ancient stars in the iron of our blood, the calcium of exploded supernovae in our bones, and the carbon and oxygen from countless stellar furnaces in every organic molecule of our bodies. We are literally children of the stars, made of stardust. And those children can now, like grown progeny, look back and study their parents, the stars, and grandparents, the galaxies, the Big Bang. This unity of origins gives us a connection to everything. We are not separate from the universe. We are portions of it, inextricably linked. The laws of physics that formed a galaxy also form the neurons in our brain that fire when we gaze at a galaxy. With knowledge, however, comes the humbling realization of how much we don't know. Our journey through cosmology answers many questions, but raises others. Why is there something rather than nothing? Did time begin with the Big Bang, or is there a multiverse with different realms beyond ours? What is the true nature of space and time on the smallest scales? Are they quantized into discrete bits, as some theories like quantum gravity suggest? We don't yet have a fully unified theory of quantum mechanics and gravity. Thus, the exact first moments of the Big Bang, the Planck time, and what happened before inflation remain mysterious. We still do not know what dark matter is, despite it making up most of the matter in the universe. We still do not know why an early hyperinflation happened, or if it's even the final answer to the early universe's smoothness and flatness. We aren't sure if dark energy is truly constant or has subtle variations, and the nature of dark energy, why vacuum has the energy it does, is deeply perplexing. In fact, theoretical physics calculations of vacuum energy overshoot observations by an outrageous factor, a major puzzle. We do not know if life is a common cosmic phenomenon or an extremely lucky fluke confined to Earth. We have not yet detected signals from other civilizations, though projects like SETI are listening. We do not know the fate of humanity, whether we will spread to the stars or remain bound to our lovely, pale blue dot. In short, we still float on a sea of mystery, with islands of knowledge gained so far. Standing at this precipice of knowledge and mystery, one cannot help but feel a profound awe. The universe is ancient and vast beyond comprehension, yet here we are, small creatures with curious minds, capable of tracing its story from the primal fireball to the present, and even forecasting its possible futures. That story, from the simplicity of the early fireball to the complexity of a living world, is both humbling and inspiring. The cosmos is breathtaking, not just in scale, but in the way it has produced patterns and coherences. The periodic table of elements forged in stars, the spiral patterns of galaxies, the double helix patterns of DNA that allowed creatures like us to emerge. There is a deep harmony in how the same physical laws apply across all scales. The nuclear reactions blazing in the core of a distant star obey the same physics as the glow of your reading lamp. The gravity that makes a planet orbit the sun is the same gravity that makes galaxies dance around one another in clusters. Mathematics, abstract patterns of logic, proves to be an incredibly effective language to describe these laws, suggesting a wondrous connection between the human mind and the workings of the universe. It's as if the universe has a hidden symmetry or order that we can glimpse through mathematics and science. Our journey of understanding is far from over. Each new discovery in astronomy or physics tends to open new questions. When we discovered the expansion of the universe, we were led to ask about the beginning, Big Bang, and the ultimate fate. When we found the cosmic microwave background, we were led to the idea of inflation. When we observed unexpected galaxy rotations, we hypothesized dark matter. When we measured distant supernovae, we stumbled upon dark energy. Every time we peel back a layer of reality, there is another layer waiting, sometimes with stranger questions. This is the beauty of science and exploration, a continuous unfolding story, each chapter building on the last, but the book seemingly without end. Picture the cosmic timeline as a grand narrative, a story that begins with nearly featureless energy and evolves into intricate worlds and beings. It's a story that spans 13.8 billion years and perhaps will span trillions more. To grasp our place in this timeline, imagine compressing the entire history of the universe into a single calendar year. The Big Bang happens at the stroke of midnight on January 1st. By early February, the first stars ignite. By mid-March, galaxies are forming. The Milky Way might form around May. Our Sun and Earth appear roughly in early September on this cosmic calendar. Life arises on Earth by late September. Complex multicellular life proliferates in November. Dinosaurs roam the Earth on December 25th, Christmas Day, and go extinct on December 30th. Modern humans emerge only in the final hour of New Year's Eve, and all of recorded human history flashes by in the last seconds before midnight. In those final seconds, we develop agriculture, build the pyramids, invent the telescope, land on the moon, and contemplate the Big Bang. When the clock strikes midnight to herald a new cosmic year,
Perhaps that represents some distant future state we've yet to comprehend. This cosmic calendar shows just how young we are. Human civilization is an eye blink in cosmic time, and even the Earth is a relatively late chapter in the story. We arrived at the tail end of the year, so to speak, but armed with curiosity and intellect, we busied ourselves in those last seconds learning about all that came in the months before us. Now we, ephemeral yet mindful, look to the future. We wonder what's next for the universe and what's next for us. Barring extraordinary intervention, the universe will continue to expand and evolve according to the physical processes we have discussed. As for humanity, we too are subject to cosmic forces, but have some say in our destiny if we are wise. We may spread to other planets, carrying our legacy of curiosity with us beyond Earth, ensuring that life and consciousness have a longer future than our single planet's fate. We may find ways to harness new energy sources or manipulate space-time, ideas once in the realm of science fiction, but who knows what knowledge awaits in the coming millennia. Or we may struggle and someday perish, becoming a brief spark that faded out. But even if our particular lineage ends, perhaps other intelligences elsewhere will carry on, or new intelligences might evolve from what we leave behind, intelligent machines, or new species. The desire to know and to wonder might itself be as resilient as life. From the standpoint of the universe, meaning is not something handed down from the stars. It is something we create. We infuse the cosmos with meaning by contemplating it. A galaxy 100 million light-years away has no idea of its grandeur, but we know, and in knowing and seeing beauty in it, we give it meaning, at least to us. In a way, the cold equations of physics blossomed into the warmth of human experience and inquiry. The universe is often described as a cold, uncaring place, and physically it is vast and mostly inhospitable. But through us, it cares about itself, in the sense that we care and we are part of the universe. This connection may be philosophically subtle, but it is emotionally powerful. Our exploration is ongoing. Even now, new telescopes like the James Webb Space Telescope peer into the distant past, seeing galaxies forming just a few 100 million years after the Big Bang, giving us new data points in the cosmic saga. Particle accelerators, like the Large Hadron Collider, probe higher energies, trying to recreate conditions just after the Big Bang, searching for clues of new physics. Perhaps particles that could explain dark matter or hints of extra dimensions. Experiments in deep mines attempt to catch a glimpse of dark matter particles zipping through Earth. Space probes explore planets and moons, looking for signs of past or present life beyond Earth. Mars's ancient riverbeds, the subsurface ocean of Europa, the methane seas of Titan. We are, in a sense, turning over every stone we can in this universe to piece together the puzzle of reality. Standing on the precipice of all this knowledge and mystery, we feel both incredibly small and incredibly enriched. The night sky no longer just offers twinkling points of light. It is a time machine, showing us distant galaxies as they were eons ago and connecting us to the moment of creation. The ground beneath us is not just dirt, it's ancient cosmic debris, a mix of elements made in star cores, arranged by geological and evolutionary processes into our immediate environment. We, the curious specks of the universe, will keep lighting candles in the cosmic dark, striving to illuminate more of that everything, even as it continually surprises us. The quest goes on, and the wonder deepens. To be alive as a human at this moment, to have consciousness, to have the accumulated knowledge of generations at our fingertips, and the ability to extend that knowledge, is a precious, fleeting gift. Through our minds, the universe has awakened to a sense of itself, however partial. We have the privilege of witnessing this vast tapestry and the responsibility of carrying that knowledge forward. In the end, the story of the universe is not just a tale of matter and energy moving heedlessly. It is also a human story, a story of awareness and curiosity finding a foothold in a vast cosmos. We began this journey meditating on the concept of everything. Now,
At journey's end, we realize that perhaps we have only scratched the surface of everything. We close with more questions than we started, but also with a deeper reverence for existence. We sense that the strangeness and wonder of the universe will never end, no matter how much we discover. As long as there are beings curious enough to look up and ask questions, the cosmos will continue to inspire. In its darkness and its light, its simplicity and its complexity, its silence and its stories, the universe offers an endless well of awe. It is a beauty we could pursue forever and never exhaust, or without end. In the darkness between the stars, a single light is failing. Once it shone brilliantly, a beacon of warmth in the cosmic night, but now it flickers with a fragile, unsteady glow. The star is dying. For millions of years it burned in a delicate balance, its fierce nuclear heart pushing outward against the relentless inward pull of gravity. It may have warmed planets, illuminated nebulae, and been a sun to some distant world, but nothing in this universe is truly eternal. Now its fuel is nearly gone, and that balance has tipped. Deep inside the star's core, the furnace that sustained it is running out of flame. There is a hush where once there was the roar of fusion. Gravity, ever patient, tightens its grip, squeezing the core harder and hotter in a desperate last attempt to keep the lights on. The star trembles on the brink. Its outer layers, once held taut by the pressure of light from within, begin to slide inward under gravity's command. If we could hear across the vacuum of space, we might catch a deep, forlorn groan as the star's very structure gives way. In one final, agonizing moment, the core of the star collapses. Ages of stellar life are undone in less than a heartbeat. Matter, that was the star's heart, is suddenly rushing inward at a significant fraction of the speed of light. Atoms are smashed together, nuclei are crushed, and the temperature spikes to unimaginable levels. It's as though an enormous weight has slammed down on the star's core, squeezing it to a fraction of its former size. Then, like a compressed spring uncoiling, all that pent-up energy is released. In that instant, the star that had faded now explodes in a blaze of glory. A flood of energy bursts outward from the core. What was moments ago a dimming ember becomes a sudden supernova, a titanic explosion of light and matter. The star's outer layers, which were collapsing inward, are blasted back out into space. In the span of a single second, a celestial object the size of a sun is torn apart. The darkness of a quiet cosmic night is pierced by a bloom of brilliance. The dying star outshines its entire galaxy, a flare of radiance against the void, like a colossal flower unfolding in fire. Anyone watching from a nearby world would see their night sky ignite with a light greater than 1,000 suns. For a brief time, this supernova shines with ferocious intensity. Gases that once formed the star's flesh are hurled into space as glowing shreds. Petals of stellar material, incandescent hydrogen, helium, and new forged heavier elements expand outward in great filamentary veils. And then, as suddenly as it began, the brilliance starts to fade. The explosion exhausts its initial energy and begins to settle. Where once there was a star, there is now a vast, ghostly cloud expanding through space. In its center, a tiny, fiercely hot remnant may persist, perhaps the collapsed core, transformed into a dense neutron star, or perhaps nothing visible at all if even the core succumbed to an all-consuming collapse. The light of the supernova dims from blinding to merely luminous and continues to wane over weeks and months, until to most eyes, the sky returns to its familiar darkness. The star is gone. All that remains is an expanding shell of gas, a nebula glimmering faintly with the last light of the star's dying breath, and, if the star's heart survived, a small, strange object hidden at the center of that nebula. In the silent aftermath, the cosmos is quiet again. Yet in that silence lies not just an ending, but a new beginning written in the ashes. The materials ejected by the star are mixing with the interstellar medium, ready to become part of something new. Every star's death is written by the life that led up to it. To understand this final blaze of glory, to truly grasp why the star had to die and how its death will give rise to new light, we must step back and watch how a star lives. Only then can we appreciate the full story, how a star's life creates the conditions for its death, and how even in dying, a star brings new light to the universe. Eons before that final eruption, our star's story began in darkness, a different kind of darkness, filled with promise. In a cold, dense cloud of gas and dust adrift in the galaxy, something subtle but significant occurred. Perhaps the passing shockwave of an older star's supernova swept through the cloud, or two galaxies brushed past each other and stirred the cosmic dust. Whatever the trigger, a region of the nebula began to condense. Gravity, the same force that would eventually destroy our star, was the midwife at its birth. What began as a diffuse, invisible patch of hydrogen gas slowly gathered into a tighter clump. As the gas particles drew closer together, their mutual gravity grew stronger, pulling in more and more material. The cloud fragmented into pockets. One of these pockets would become our star. Within that shrinking globule of gas, matter rushed inward, and the density and temperature at the core of the clump soared. At first, it was just a protostar, a warm, thick knot of gas still shrouded by the cocoon of dust from which it formed. The newborn protostar did not yet shine with its own light in the visible spectrum, but it was heating up steadily. As it grew in mass, pulling in material from the surrounding nebula, it began to spin faster, much as a dancer spins faster when pulling in their arms. A swirling disk of leftover gas and dust flattened around it. Occasionally, the protostar's growth was so violent that it ejected some material back out along its poles in narrow jets, like cosmic geysers, carving through the surrounding gloom. If we could have seen inside the nebula, we might have observed multiple such protostars forming in a cluster, siblings born from the same cloud, each gathering their own disks. Our protostar, for a time, was just one glowing embryo among many in a stellar nursery. Gravity kept squeezing that protostar's core, tighter and hotter, until one day, after perhaps millions of years of slow compression, the temperature at the center crossed a critical threshold. The star's heart caught fire. Hydrogen atoms, which had been pressed together more and more fiercely, suddenly began to fuse with one another. 4 hydrogen nuclei merged into one helium nucleus, and in that transformation, a tiny fraction of mass converted into a tremendous amount of energy. This was the moment of birth. The protostar's hidden fire ignited into starlight. The cocoon of dust was blasted away by the newborn star's radiance, and it announced itself to the universe as a new sun. The star settled into a long adulthood, blazing contentedly in a steady golden glow, if it was of moderate mass like our sun, or maybe a brilliant blue-white if it was much more massive, or a dim red if it was smaller. Its core became a powerhouse of fusion, turning hydrogen into helium and flooding the interior with energy. That energy pushed outward as light and heat, creating pressure that held up the star's weight. Gravity pulled inward, thermonuclear fire pushed outward. The two forces balanced in a beautiful, stable harmony. Astronomers call this hydrostatic equilibrium, but one might simply think of it as the star's heartbeat, a steady outflow of energy keeping gravity's crush at bay. For the majority of a star's life, this balance persists. Our own sun, for example, has been in this stable phase, the main sequence, for about 4.5 billion years, and will continue similarly for about 5 billion more. During this time, the star changes very little to the casual observer. It shines with a nearly constant brightness, day after day, century after century, its surface seething and churning, but its overall output steady. If the star has planets around it, they bask in this steady glow. Life, as on Earth, might have the chance to arise and evolve under the star's reliable warmth. Yet even a star's life, though long compared to ours, is not truly eternal. The fuel in its core is finite. The larger and hotter the star, the faster it burns through its supply. A truly massive star, dozens of times heavier than the Sun, might exhaust its core hydrogen in only a few million years, an eye blink compared to the Sun's 10 billion-year lifespan. A tiny red dwarf star, on the other hand, sipping its fuel frugally, can shine for hundreds of billions of years. But eventually, in every star, the day comes when the hydrogen in the core is mostly spent. The core, now largely helium ash, can no longer sustain the same rate of nuclear burning. The outward pressure begins to falter, and gravity starts to gain the upper hand. The star has reached the end of its youth and stands at the threshold of its first great crisis. The first sign of a star's impending death is a profound transformation. As the core's fusion ebbs, nothing is left to hold up the weight of the star's outer layers. Gravity pushes those layers inward, compressing and heating the core once again. Paradoxically, this new squeeze of gravity provides a temporary lifeline. Around the inert helium core, a shell of hydrogen, which was previously too cool to fuse, now becomes hot enough to ignite. The star gains a second wind. Hydrogen fusion resumes in a shell around the core, pumping out energy furiously. This causes the outer layers of the star to swell outward. The star's radius balloons to many times its former size. As the surface expands, it cools and reddens, much like a piece of metal glows red when cooler but white when very hot. The once steady yellow star becomes a red giant, bloated and luminous, but cooler on its surface, with a heart of helium ash hidden at its center. If this star once had orbiting planets, their fate is precarious. During its expansion, the star's atmosphere reaches outward dramatically. A world that was once comfortably distant may now be inside the star's tenuous outer layers. Mercury and Venus, for instance, will be engulfed when our Sun becomes a red giant. Earth may or may not be swallowed whole. Some calculations suggest Earth might spiral outward due to the Sun's mass loss, just evading direct consumption. But even if it isn't engulfed, it will be scorched beyond recognition. In either case, the inner worlds will be burned and likely destroyed. Imagine for a moment being on a hypothetical moon of a distant gas giant, watching this happen. Over thousands of years, your sun grows ominously larger and redder in the sky. By the end, it spans a huge portion of the heavens, a dim red Goliath casting an eerie copper glow. The heat is relentless. Oceans boil away, atmospheres escape, surfaces melt. The gentle star that nurtured life has transformed into a ruthless juggernaut. Inside the red giant, while the outer layers swell and cool, the core is contracting and heating. When the temperature and pressure in the helium core become high enough, a new kind of fusion begins. Helium nuclei start fusing into carbon and oxygen. For a star like the Sun, this onset of helium fusion can be sudden, a phenomenon called the helium flash, where the core ignites in a runaway burst of energy, though the energy is absorbed and does not blow the star apart. In more massive red giants, helium ignition is a more sedate onset. Either way, the star now has a new fuel. For a while, helium fusion in the core provides an internal energy source, which somewhat stabilizes the star again. The star's radius might shrink slightly, and its surface temperature might increase for a time, especially in stars a bit more massive than the Sun, which forms something called a horizontal branch state. For a period of time, the star finds a bit of equilibrium once more, quietly burning helium to carbon and oxygen in its center. But this reprieve is relatively short-lived on cosmic timescales. A star like the Sun will burn helium in its core for only a few tens of millions of years, a mere flicker compared to the billions of years it spent burning hydrogen. Eventually, the helium too is exhausted. And this time, the star's core is left with carbon and oxygen, elements that for a modest-sized star are effectively inert. The core is not hot enough to fuse them into heavier elements. Fusion grinds to a halt in the center once more. The inert carbon-oxygen core, incredibly dense and hot, continues to contract under gravity. But now something quantum mechanical and strange comes into play. The core's atoms are packed so tightly that the electrons, in effect, refuse to be squeezed any further. They generate a quantum pressure, electron degeneracy pressure, that halts the collapse. The core, perhaps the size of Earth, but with half the Sun's mass, is as compressed as it can get, without triggering further fusion or collapse. Meanwhile, the star's outer layers have become unstable. Without a vigorous energy output from the core, nothing can hold on to those distant layers. In the star's final breaths, it begins to pulsate. With each pulsation, it coughs away great shells of its own gas into space. Gentle stellar winds grow into intense gusts, pushing the star's envelope outward. The red giant sheds its skin, layer by layer. Over some thousands of years, the star loses a significant fraction of its mass this way. What remains at the center is the hot, naked core, now exposed for the first time to the outside universe. The escaping outer layers form an expanding cloud around it. The core is fiercely hot, hundreds of thousands of degrees, and its ultraviolet radiation causes the receding gas to fluoresce. What was once the star's atmosphere now becomes a gorgeous planetary nebula, a glowing shell of multicolored gas stretching out into the void. These nebulae are among the most beautiful objects in astronomy. They take on fantastical shapes, sometimes a nearly spherical bubble, other times a bipolar structure like two facing cones, and often complex rings and halos. To early astronomers with small telescopes, some resembled the round shapes of planets, hence the name planetary nebula, though they have nothing to do with planets. Our dying star's cast-off layers might form a luminous ring or an intricate lace-like web. As the ultraviolet light from the central core floods outward, it excites different elements in the gas. Hydrogen glows red, oxygen glows green-blue, nitrogen can add touches of red as well. The nebula may appear as a haunting turquoise halo or a delicate rosy sphere embedded with filaments. Some planetary nebulae appear as if a cosmic iris had opened its eye in the depths of space, with the central star as the pupil. These structures are often symmetric and eerily beautiful, expanding at tens of kilometers per second into the surrounding darkness. Such a nebula doesn't last long, a mere few tens of millennia, before dispersing into the wider galaxy. As it expands, its gases cool and dilute, fading from view. One day, not far by cosmic standards, the nebula will merge back into the interstellar medium from which the star once formed. But while it shines, it creates an unforgettable tableau, the farewell gesture of a star like our Sun. At the center of the expanding nebula lies what's left of the star's core, a white dwarf. This object is the smoldering ember of the star, incredibly hot at first but destined only to cool over time. It is a sphere of carbon and oxygen about the size of Earth, but containing roughly half the mass of the Sun. A teaspoon of its material on Earth would weigh tons. Inside this dense core, matter is supported by electron degeneracy pressure. The electrons crowding each other provide the stiffness that prevents further collapse. The white dwarf is initially bluish-white from the immense heat of its exposed interior. With no nuclear fusion to replenish its energy, those fires have gone out forever. It simply radiates away its stored thermal energy into space. Over billions of years it will fade from white to yellow to red, and eventually become utterly dark. At that final stage, it is sometimes called a black dwarf, a cold, inert cinder in which even the residual glow has died out. However, the universe is not yet old enough for any black dwarfs to exist. Our star's white dwarf will shine, albeit weakly, for longer than the current age of the universe before it truly goes black. There is a poetic notion that as a white dwarf cools, its carbon might crystallize like a gigantic diamond. In fact, observations hint that some old massive white dwarfs have partially crystallized interiors. One could imagine that in the far future, the core of our sun might become a diamond the size of Earth, drifting through the galactic night. For now, our white dwarf is still extremely hot and luminous in ultraviolet and X-rays, which is what lights up its planetary nebula. Over time it will fade, but during the nebula's brief glorious existence, the white dwarf is a brilliant pinpoint at the center, a cosmic tombstone marking where a star's heart remains. This is the fate that awaits our sun and other stars of similar mass. A gentle, if somewhat melancholy, end, a final flowering as a nebula, and the quiet retirement of the core as a white dwarf. No spectacular explosion destroys the star outright. Instead, it is a slow shedding of worldly goods, a final display of color and light, then a gradual fading into the night. It is a quieter death than the ferocious supernova we imagined earlier. Yet, from the perspective of the universe, even this mild death has great significance. The outer layers shed into space carry elements that the star forged in its later life, elements like carbon and nitrogen, produced during the red giant phase. These become part of the raw material for future stars and planets. The star's death, though calm, seeds the cosmos just as surely as a supernova does, if in a more modest way. In dying, the star gives back much of its substance to the galaxy. Still, one might ask, what if a star had been born much more massive? Not all stars go gentle into that good night. For those born with significantly more mass, 8, 10, or 20 times the mass of the Sun or more, the final act is far more violent. When a high-mass star exhausts its core hydrogen, it, too, balloons into a supergiant, a red supergiant if relatively cool, or possibly a yellow or blue supergiant depending on its mass and stage. Inside, it goes through a furious sequence of burning stages. Unlike a low-mass star, a massive star can fuse elements beyond helium because its core gets hot enough to ignite heavier and heavier fuel. After helium is used up, creating carbon and oxygen, the core contracts and heats until carbon can fuse, producing neon, magnesium, and other elements. When carbon is depleted, the core, now largely neon and oxygen, contracts and ignites those. Neon fuses to oxygen and magnesium. Oxygen later fuses to silicon and sulfur. Silicon eventually burns to produce iron. The star's interior becomes layered like a giant onion, concentric shells where different fuels are burning. Hydrogen in an outer shell, helium in a shell beneath that, carbon, oxygen, neon, and so on, with an iron core forming at the center. Each successive stage of fusion burns faster than the last. A process that took millions of years for hydrogen and hundreds of thousands for helium takes mere centuries for carbon, then only years for neon, months for oxygen, and perhaps days or even mere hours for the final burning of silicon into iron. The reason is that as the star steps up the ladder of elements, the efficiency of energy production drops, so it has to burn through the fuel much faster to sustain itself. Finally, the star's core is composed of iron and nickel nuclei. And here the chain of fusion terminates, because iron is a dead end in terms of energy. Fusing iron into heavier elements does not release energy. It actually consumes energy. The star has no more nuclear fuel that can produce an outward push. The iron core grows to a critical mass, about 1.4 times the mass of the Sun, though compacted into a sphere only perhaps the size of Earth. At that critical point, the core can no longer support the tremendous weight of the star's envelope pressing down on it. In less time than the blink of an eye, the core collapses. Gravity wins decisively, catastrophically. The core's atoms are crushed together so forcefully that electrons are shoved into protons, turning them into neutrons and neutrinos. The entire core, which moments before was the size of a small planet, implodes to a sphere perhaps only a couple of dozen kilometers across, like a city-sized ball of neutrons. This collapse happens with incredible speed, less than a second. The infalling material reaches densities similar to an atomic nucleus. It's as if an object the size of the Earth suddenly became the size of a city. The violence of it is difficult to imagine.
The collapse is eventually halted by the hard core of neutrons. Think of it like a rubber ball hitting a wall. The core bounces a little, sending a shock wave outward. At the same time, in that brief moment of formation, the new neutron core releases an immense burst of neutrinos. These ghostly subatomic particles rarely interact with matter, but so many are produced, carrying off about 99% of the collapse energy, that they impart a shock to the overlying stellar material. The combination of the rebound and the neutrino blast causes the star's infalling layers to explode outward. The result is a titanic supernova explosion, the same kind of event we described at the beginning. The outer parts of the star, by now expanded into a supergiant, are blown off in a tremendous blast, racing into space at a significant fraction of the speed of light. The energy released is almost unimaginable. For a brief period, the exploding star can radiate more energy than all the billions of other stars in its galaxy combined. If such a supernova occurred within a few dozen light years of Earth, it could disastrously affect our biosphere. Fortunately, no star currently that close is poised to explode in this way. The nearest candidate, Betelgeuse, is about 600 light-years away. But even at thousands of light-years, a supernova can be visible to the naked eye. Historical records around the world tell of new stars appearing in the sky. These were supernovae in our own galaxy. In 1054, observers in East Asia, and possibly North America, according to some petroglyph interpretations, recorded a brilliant star in the daytime sky. Unknown to them, they were witnessing a supernova whose remnant is the Crab Nebula. In 1604, astronomers observed another bright supernova, later called Kepler's supernova. Those events were in our Milky Way. Supernovae in nearby galaxies have also been visible to the naked eye, such as one observed in 1987. If Betelgeuse were to explode, future generations would see a star as bright as the moon for weeks on end, a celestial beacon announcing the death of a supergiant. As the star explodes, profound things happen inside the blast. The high temperatures and rapid changes trigger nuclear reactions that create new elements. All the elements heavier than iron that the star couldn't produce during its life are now synthesized in the furnace of the explosion. Gold, for example, and iodine, uranium, and many others are forged in seconds by rapid neutron capture and other processes. These precious metals and heavy elements are incorporated into the ejected gas that races outward. The debris of the star enriches the surrounding space with a myriad of elements that did not exist in such abundance before. And what of the star's core? After the supernova, if the core's mass is below a certain threshold, around 1.5 to 2 times the Sun's mass, it stabilizes as a neutron star, a city-sized, ultra-dense object made mostly of neutrons. If the core is above that threshold for very massive stars, not even the neutron pressure can hold it up, and it continues to collapse into a black hole, a region of space-time with gravity so strong that not even light can escape. Thus, the ultimate fate of the core is decided by the star's mass, neutron star or black hole. In either case, neutron star or black hole, something astonishing remains where the heart of the star once was. Meanwhile, the rest of the star has been blasted into space, forming a supernova remnant that will expand and fade over thousands of years. A core collapse supernova is one of the most magnificent events in nature, the violent death of a massive star. It is an ending on a grand scale, sudden, forceful, and final. And yet, in that destruction lies a kind of creation. The supernova scatters heavy elements,
elements that will someday become part of new stars, new planets, perhaps new living beings. Without such supernovae, the universe would lack most of the complex atoms that make up planets and life. So, the star's death, though a dramatic annihilation, is far from pointless. It is, in a sense, sacrificial, a star giving back to the cosmos all the elements it forged in life, and even creating new ones in death, fertilizing the galactic fields for the generations to come. Now let us consider this elemental alchemy more broadly. How, over the history of the universe, stars have served as the forges of the elements. From the hearts of living stars to the violence of their deaths, the chemical elements that compose our world and our bodies have been built up. In addition to hydrogen and some helium, which came from the Big Bang, all other naturally occurring elements were synthesized by stars. Stars in their long, stable lifetimes fuse lighter elements into heavier ones. In their cores, hydrogen becomes helium. When hydrogen is exhausted, helium fuses into carbon and oxygen. Later, in massive stars, carbon may fuse into neon and magnesium, oxygen into silicon, and silicon into iron. These processes happen over millions of years inside stars and produce most of the elements up to iron on the periodic table. The next time you glance at a periodic table, know that each element there has a cosmic pedigree: carbon, oxygen, nitrogen. These were made in star cores. Elements like silicon and sulfur in supergiant stars. Iron produced in the last gasp of a massive star's life.
What about elements heavier than iron, such as gold, lead, platinum, or uranium? These require special, extremely energetic conditions to form. Many are created during supernova explosions, when the flood of neutrons and the intense energy allow atomic nuclei to capture neutrons rapidly and build up into heavy elements, a process called the R process. Still others, especially some of the heaviest like gold and platinum, are now thought to be primarily forged in the colossal explosions that occur when two neutron stars collide. We'll talk about those later. There are also slower processes in aging giant stars, the S process, that builds certain heavy elements over longer periods and gently disperse them via stellar winds. But in general, the universe's inventory of elements beyond iron has been greatly enhanced by violent deaths, supernovae, and neutron star mergers. Consider some examples of this cosmic alchemy. The iron in your blood's hemoglobin was forged in the core collapse of a massive star long before the Earth formed. The oxygen you breathe was cooked in the core of an ancient star and later scattered into space by a stellar wind or explosion. The calcium in your bones was built up in a giant star and cast off in its old age. Carbon, the backbone of life's chemistry, was created by the triple alpha fusion of helium in the core of a red giant star. Even rare elements like iodine, essential to biology in trace amounts, or gold, treasured and malleable, have origins in stellar cataclysms. Iodine likely in supernovae, and gold in the mergers of neutron stars that send debris rich in precious metals into space. Every atom of every element heavier than hydrogen that we find on Earth and in our bodies has traveled through a star. We are, quite literally, made of stardust. The very first generation of stars in the universe, billions of years ago, soon after the Big Bang, had only hydrogen and helium to work with. They forged the first heavy elements and spread them around via supernovae. Subsequent generations of stars were born from gas clouds already seeded with those heavier elements, which meant those stars could produce even more complex elements when their turn came. Over cosmic time, each cycle of star birth and death has enriched the galaxies further. By the time our solar system formed about 4.6 billion years ago, the gas and dust from which the sun and planets condensed were laced with the output of countless prior star deaths. That is why Earth has a crust rich in silicon and iron, why we have water, oxygen plus hydrogen, why there is phosphorus and potassium and all the rest, because the materials had been pre-cooked in stellar furnaces. It's an astonishing connection.
The existence of our planet and of us living beings is directly tied to stars that died before the sun was born. We think of those stars as long dead and gone, and they are. But their chemical gifts live on in everything we see around us. In a sense, those ancient stars are not truly gone because we remember them with every breath and every bite of food. Our very bodies are their memorial. We truly are made of star stuff. This isn't just a romantic notion, but a physical fact. The atoms that compose our bodies were assembled in stellar cores and distributed by stellar winds and explosions across the galaxy, later to clump and form new worlds and living creatures. The death of stars is intimately tied to the creation of the ingredients of life. Every death, in this cosmic sense, is a kind of rebirth elsewhere. A star once existed for billions of years and then perished, returning its substance to the universe in a moment. And from that substance, new life eventually emerged. It's humbling and ennobling all at once. We are the universe's way of recycling stellar material into consciousness. In dying, stars both destroy and create. They leave behind remnants, like white dwarfs or neutron stars, and scatter their enriched guts across space. Yet not everything of the star is lost in this process. Even as a supernova strews a star's outer layers across the galaxy, the core of the star often survives in a drastically altered form. From the wreckage emerges a stellar remnant that challenges our understanding, an object so dense and extreme that it's like nothing else in the universe. Now, we turn to one such remnant, the neutron star, to witness what becomes of a massive star's heart after the explosive fury of a supernova. Imagine a ball of matter roughly 20 kilometers, 12 miles, across, about the size of a city. Now imagine that this tiny sphere contains more mass than 1.5 suns. This is a neutron star. It's essentially the collapsed core of a massive star, compressed so much that atoms can no longer remain atoms. The crushing gravity forces electrons and protons to combine into neutrons, hence the name neutron star. The entire object is basically a single giant atomic nucleus, an enormous clump of neutrons packed together with incredible density. A neutron star's density defies common sense. A teaspoon of neutron star material would weigh billions of tons on Earth, roughly the mass of a mountain crammed into a spoon. The surface gravity of a neutron star is similarly mind-boggling, hundreds of billions of times stronger than Earth's. If you were to drop a pebble from a height of 1 meter above a neutron star's surface, it would hit the surface in a microsecond and release as much energy as a large bomb. Standing on such an object, if one could, is an impossibility. You would be flattened thinner than a sheet of paper by the gravity. Everything about neutron stars is extreme. The gravity not only crushes matter, it also warps space and time around the star. Light leaving the surface is redshifted, reduced in energy, by the struggle against gravity's pull. If you observed a neutron star up close, its intense gravity would act like a lens, bending the path of light. You could actually see parts of the far side of the star as bent light curving around it. Neutron stars also spin, often at astonishing speeds. The core of the star that became the neutron star was rotating, and as it collapsed, it conserved angular momentum, like a spinning ice skater pulling in their arms. What was a rotation of maybe 1 revolution per day can become 1 revolution per millisecond. Indeed, many neutron stars spin tens or hundreds of times per second. The fastest known spins around 716 times a second. These rapid rotators are called pulsars when they emit detectable beams of radiation. A neutron star typically has a strong magnetic field, inherited and amplified from the star's original magnetic field as it collapsed. If the magnetic axis is not aligned with the spin axis, the rotating magnetic field accelerates charged particles and produces beams of radio waves, and sometimes X-rays or gamma rays, that shoot out along the magnetic poles. As the star spins, these beams sweep around like cosmic lighthouses. An observer in the path of the beams will see the star pulsing on and off, hence the name pulsar. The first pulsars were discovered as very regular radio pulses, so precise that at first astronomers half-jokingly dubbed them LGM for little green men, thinking perhaps they were signals from an intelligent civilization. We now know they are one of the natural marvels of neutron stars. The magnetic fields of neutron stars can be unimaginably strong. The most magnetic ones, called magnetars, have fields about 1 trillion times stronger than Earth's magnetic field. Such a field can distort the electron clouds of atoms from thousands of kilometers away and would erase a credit card on Earth from a distance halfway to the moon. If you somehow approached a magnetar, the magnetic forces would not only scramble your compass, they would disrupt the very molecular bonds in your body. Magnetars occasionally experience starquakes. Their intense magnetic fields put so much stress on the solid crust of the neutron star that it fractures. When a magnetar's crust cracks, the reconfiguration of the magnetic field can release a burst of high-energy radiation. In 2004, a magnetar on the other side of our galaxy erupted and bathed Earth in gamma rays. For a fraction of a second, that single neutron star flare outshone all the stars in the Milky Way. Neutron stars may be small, but they are powerhouses of strange and violent phenomena. Though a neutron star has no more fusion and is technically a dead star, it is far from inert. It begins its life immensely hot, trillions of degrees right after formation, cooling to millions of degrees fairly soon. It emits thermal radiation, mainly X-rays when young, and will take millions of years to cool to more normal temperatures. As mentioned, many emit beams as pulsars. They gradually slow down as they radiate energy. Over very long times, an isolated neutron star will cool and its pulses will weaken, making it harder to detect. These become so-called quiet neutron stars, basically cosmic cinders a few dozen kilometers wide. But even then, if such a collapsed star encountered another star or gas cloud, it could spring into action again by accreting matter and flaring up in X-rays. Neutron stars are like celestial tombs. They contain within them the remnants of a star's core, all its complexity crushed into a hyperdense state. They challenge our understanding of physics, matter on the verge of collapsing into a black hole. In fact, if you were to add just a bit more mass to a typical neutron star, piling on a few more tenths of a sun's worth, you could force it to collapse further into a black hole. They are right on the knife's edge, between existence and oblivion. And this makes them fascinating waypoints in the story of stellar death. They are not the absolute end, but a transformed state of matter, a stepping stone toward the most extreme phenomenon of all. Even more extreme than a neutron star is the fate of the most massive stellar cores, the birth of a black hole. If a stellar core has more than about 2.5 to 3 solar masses after a supernova, gravity overwhelms all possible forces that might hold the core up. The neutrons in a neutron star, which normally resist further compression, themselves succumb if the mass is too great. There is no known force in the universe that can support such a massive core against collapse, so collapse it does, all the way, effectively, to a point of infinite density, a singularity in theory. A black hole is an object, or rather a region of space-time, formed by this total collapse. Around the collapsing core, a boundary forms called the event horizon. This is not a physical surface, but a spherical region of space around the singularity where gravity's pull is so strong that escape velocity exceeds the speed of light. Anything, including light, that comes within this horizon is trapped and inevitably drawn into the center. From the outside, the event horizon is the point of no return. It's as if the core has punched a hole in the fabric of the universe and disappeared. All that's left is an intensely gravitational presence. A black hole that comes from a star
might contain a mass of, say, 5 or 10 suns, but the event horizon radius would be only on the order of a few tens of kilometers. For comparison, Earth's radius is about 6,400 kilometers. Imagine an object 10 times more massive than the Sun, crammed into a sphere the size of a small city. That is the scale of a stellar black hole. At the event horizon, not even light can escape, so by definition, the black hole is perfectly black. If you were viewing a black hole from a safe distance against a field of stars, you might notice a strange warping or bending of the background starfield as their light detours around the black hole's gravity. But otherwise, you'd see only blackness in the region of the hole, hence the name. What happens if something, say, an unlucky spaceship or star, gets too close to a black hole? Tidal forces become extreme. Much like the moon causes ocean tides on Earth by pulling a bit differently on the near side versus the far side, a black hole's gravity can vary tremendously over short distances. For a small black hole, for instance, the gravity at a distance of, say, 1,000 kilometers from its center might be millions of times stronger than the gravity 1,100 kilometers out. That difference would stretch any infalling object into a long, thin shape. Scientists grimly term this process spaghettification. A person falling feet first toward the black hole would feel their legs being pulled much more strongly than their head, and the result would not be survivable, to put it mildly. For larger black holes, like those at galactic centers, the tidal forces at the horizon might be less drastic, and one might actually cross the event horizon seemingly unharmed. But as one continued inward, the increasing gravity gradient would ultimately spaghettify and crush any object long before reaching the central singularity. Black holes also distort time. To a distant observer, a clock carried by something falling into a black hole would tick slower and slower as it neared the event horizon, and it would appear to stop entirely at the horizon. In fact, the falling object itself would never be seen to actually pass through the horizon. It would just fade and redden and freeze at the edge from the distant observer's perspective. But from the point of view of the infalling object, or person, there is no abrupt sensation at the horizon. One could cross it without fanfare, aside from those tides, and only later realize there is truly no way out. Inside, all paths lead inevitably to the center, the singularity, in a very short amount of proper time. Because no information can escape from inside the event horizon, what lies at the singularity remains one of the great mysteries of physics. Our current theories break down under those conditions of infinite density. It's possible that, in the real universe, singularities might be smoothed out by some quantum effect we don't yet understand, or perhaps they might even connect to other regions of space-time as speculative wormholes. But as far as observations are concerned, a black hole's interior is beyond our reach. From the outside, however, black holes do have measurable properties: mass, spin, and electric charge, though astrophysical black holes are typically uncharged. Many stellar black holes spin rapidly because the star's core had rotation, and that angular momentum is preserved. A rotating black hole drags space-time around with it, an effect called frame dragging. It can also power jets of high-speed particles if it's actively accreting gas. The rotational energy and magnetic fields can push some infalling plasma out along the poles. In binary systems, a black hole can tear matter from a companion star. That matter swirls into an accretion disk around the black hole, heating to millions of degrees and emitting X-rays and even gamma rays. Such systems are often detectable as bright X-ray sources. In fact, the first black holes were discovered because of their X-ray emissions in binary systems, like Cygnus X1, which alerted astronomers to a likely black hole siphoning gas from an unlucky companion star. It's ironic. A black hole itself emits no light, yet if it has a companion star or gas falling in, it can be among the brightest objects in the sky due to the energetic fireworks of that accretion. If isolated, a black hole is far harder to detect. It essentially becomes a patch of darkness. It can betray its presence only by gravitational effects,
like bending light from background stars or influencing the orbits of nearby objects. In recent years, scientists managed to image the surroundings of a black hole directly. A global network of radio telescopes acting in unison, the Event Horizon Telescope project, captured the telltale silhouette of a supermassive black hole in a distant galaxy, seen as a dark shadow against a swirl of glowing gas. For stellar mass black holes, we have not imaged any directly, but their existence is strongly inferred by many observations. Black holes, especially those left by stars, are often quiet passengers in the galaxy. Astronomers estimate there are millions of them drifting through the Milky Way, remnants of ancient massive stars, essentially invisible unless they happen to interact with something. Indeed, one such dark wanderer was recently detected when its gravity magnified the light of a more distant star in an effect called gravitational microlensing, an exceedingly rare and fleeting event that nonetheless gave us a glimpse of an otherwise invisible rogue black hole passing through the galactic neighborhood. In the end, a black hole is perhaps the strangest legacy a star can leave. The star's entire identity, its thermonuclear brilliance, its shining surface, its complex layers, are all erased, collapsed into an infinitesimal mystery. What remains is pure gravity, a warp in space-time, a trap from which nothing can return. And yet, even this is part of the life cycle of the cosmos. Black holes are not malevolent. They are simply another possible end state of stellar evolution. They even play a role in the ecosystem of the galaxy, stirring interstellar gas with their gravity and merging with each other to release new kinds of energy in the form of gravitational waves. Thus far, we have explored what happens to individual stars at the ends of their lives, planetary nebulae and white dwarfs for the smaller ones, supernovae with neutron stars, or black holes for the larger ones. But the story does not end with these remnants. These stellar ghosts, the white dwarfs, neutron stars, and black holes left behind, continue to drift through the galaxy, and though they are no longer active nuclear furnaces, they are far from irrelevant. In fact, our Milky Way is populated by billions of such remnants, and they quietly influence the evolution of the galaxy. For every star that currently shines in the night sky, there are many faded stellar corpses lurking invisibly in the dark. Imagine the Milky Way not just as a glittering river of light, but also as a vast graveyard of expired stars. White dwarfs, in particular, are extremely common. Practically every low to medium mass star that ever lived in the past 13 billion years of our galaxy's history is now a white dwarf, unless it had a companion and went supernova as a type Ia, which is less common. It's estimated there are many billions of white dwarfs in our galaxy, slowly cooling. Similarly, neutron stars populate the Milky Way in their hundreds of millions, a number gleaned from the vast number of supernovae that must have occurred over cosmic time. And black holes of stellar mass might number in the tens of millions, roaming quietly. These objects are hard to detect when they're isolated, but they are there. Their collective gravitational influence contributes to the mass of the galaxy, some of the missing mass that isn't in visible stars or gas. These stellar remnants are like ghosts, invisible to normal sight, since a white dwarf is very dim compared to a star, a neutron star often only detectable as a pulsar or X-ray source, and a black hole completely dark unless feeding. Yet, though ghostly, they still have physical effects. A white dwarf, for example, retains most of its star's mass. If it has planets or a companion star, it still exerts a gravitational pull on them. Neutron stars and black holes gravitationally tug on nearby stars if any pass too close, possibly altering orbits over millennia. In aggregate, the population of stellar remnants adds to the galaxy's mass distribution, subtly affecting the motions of stars and gas on large scales. Some stellar ghosts actively announce themselves under the right circumstances. A neutron star with a strong magnetic field spinning as a pulsar will beam radio waves into space. If Earth lies in the path of those beams, we detect a precise periodic signal, a cosmic lighthouse blinking across the void. The pulsar at the heart of the Crab Nebula, the remnant of the 1054 supernova, still powers that nebula with a wind of particles and electromagnetic fields, causing the nebula to glow in X-rays and optical light. Neutron stars can also wander through the galaxy at high speeds. Some are given a kick at birth by asymmetries in the supernova. A fast-moving neutron star plowing through interstellar gas can create bow shocks, like the shockwave in front of a speeding boat, compressing and heating the gas, leaving a trail that could one day seed new stars. Black holes, too, can make their presence known if they encounter matter. In a binary system, as mentioned, a black hole can steal gas from a companion star. That gas, swirling into the black hole, gets intensely hot and radiates X-rays. From Earth, we see such systems as bright X-ray sources. Sometimes the inflow isn't steady. Imagine the black hole biting off more than it can swallow, which can lead to spectacular X-ray flares or even jets of plasma being ejected at near light speed from the vicinity of the black hole's event horizon. We've observed such phenomena in so-called microquasars, stellar mass black holes, mimicking on a smaller scale the behavior of supermassive black holes in galactic centers. Even an isolated black hole might reveal itself by lensing the light of background stars, as mentioned, or by faintly glowing due to the accretion of diffuse gas in the interstellar medium. The combined effect of countless stellar remnants also contributes to the cosmic rays permeating our galaxy. Supernova remnants accelerate particles, protons, nuclei, electrons, to high energies. Many of those particles wander the galaxy as cosmic rays, eventually running into things like our atmosphere, where they create showers of secondary particles. Neutron stars, especially pulsars and magnetars, and black hole accretion disks, can also accelerate particles. These cosmic rays can alter the chemistry in interstellar clouds, catalyzing certain reactions, and may even affect planetary atmospheres over time. Even white dwarfs, the most silently fading of stellar ghosts, can have a later chapter under the right conditions. If a white dwarf is in a close orbit with another star, it can siphon gas off its companion. That gas can accumulate on the white dwarf's surface and episodically ignite in a burst of fusion, causing a nova, a sudden brightening of the white dwarf star system. The white dwarf remains intact, and the process can repeat, essentially a ghost star showing flashes of life by stealing from its neighbor. If the white dwarf accumulates enough mass from its companion to approach the Chandrasekhar limit, 1.4 solar masses, it could even detonate entirely as a Type Ia supernova, obliterating the white dwarf in the process. In that sense, even a dead star can, given the right circumstance, die a second death, taking part in one of the universe's grand explosions. Our galaxy's center houses the largest ghost of all, a supermassive black hole millions of times the mass of the Sun. While not a product of a single star's death, it's the result of many mergers and accretion events over the galaxy's history. It stands as an ultimate example of what gravitational collapse can lead to. This behemoth, lurking about 26,000 light-years from us, in the direction of Sagittarius, orchestrates the orbits of stars in the galactic core. Usually it's quiet, but occasionally it snags a passing star or cloud, producing energetic flares. It reminds us that even at the grandest scale, the remnants of cosmic evolution continue to shape their surroundings. Time is a key factor in how prominent these ghosts are. As millennia and millions of years pass, stellar remnants will increase in number. We live in an era when many stars are still in their shining prime, but far in the future, these remnants will far outnumber the bright stars. The galaxy will eventually become a darker place populated mostly by cooled white dwarfs, dim neutron stars, and black holes, plus diffuse gas. The living, burning stars will be few In that distant epoch, the ghosts will truly dominate the scene. For now, though, they coexist with a vibrant stellar population. They are like an unseen foundation beneath the more obvious architecture of bright stars. They quietly contribute to the cycle of matter and energy. They provide stepping stones to further cosmic events, like neutron star mergers producing new phenomena. The story of stellar death doesn't end with the initial death. It continues as these ghosts interact, decay further, or sometimes combine in spectacular ways. We've touched on a few hints of even more dramatic events when these stellar remnants meet or interact. Indeed, some of the most breathtaking phenomena in the universe occur when death begets death, when two stellar corpses engage in a final dance or collision. Not all stellar deaths occur in isolation. Many stars are born in binary systems, and their fates are intertwined. Let's explore how binary relationships can lead to unique kinds of stellar demise, cataclysmic variables like novas, the exceedingly bright Type Ia supernovae, neutron star collisions that create gold and gravitational fireworks, and other cosmic pas de deux that enrich the drama of stellar death. Consider a binary star system where one star dies before the other. For instance, imagine a sun-like star and a slightly more massive companion orbiting each other. The more massive star evolves faster, becomes a red giant, and eventually sheds its outer layers, ending up as a white dwarf, while its companion is still in a relatively normal state, perhaps a main sequence star or a red giant of its own later on. Now you have a white dwarf and a second star in a binary. The white dwarf is a tiny, dense object with powerful gravity, and if the two are close enough, it can begin pulling gas away from its still-living companion. The unfortunate companion's star finds its outer layers being siphoned off, spiraling onto the white dwarf. This transfer of mass at first might be a gentle stream, invisibly making the white dwarf more massive. But as the stolen hydrogen from the companion accumulates on the white dwarf's surface, it grows denser and hotter until, flash, the layer of gas ignites in a runaway fusion reaction. In a matter of seconds or minutes, the accumulated hydrogen burns explosively into helium. The white dwarf's surface blasts off a shell of fusion ash into space. From afar, this system suddenly appears to brighten enormously. What was a faint star may become visible to the naked eye as a new star in the sky for a few weeks. This is a nova, Latin for new star. It's not the birth of a star, of course, but rather a flash from a dead star reigniting stolen fuel. In a nova, the white dwarf survives the explosion. It's akin to a stellar hiccup, however energetic. After the blast, the white dwarf can go back to quietly accreting matter from its companion, and after some years or decades or millennia, it might erupt again. Some systems are known as recurrent novae because they flare multiple times. The cycle can continue as long as there's a supply of fresh fuel from the companion, and as long as the white dwarf's gravity can pull material in a stable manner. These nova explosions, while dramatic, are relatively small on the cosmic scale. They don't destroy the star and are minuscule compared to supernova. However, under certain circumstances, a white dwarf in a binary can undergo a far more devastating event. If the white dwarf accretes enough mass from its companion, pushing its mass closer to that Chandrasekhar limit, 1.4 solar masses, the pressure and temperature in its core can become high enough to ignite carbon fusion in an uncontrolled way. Remember, this is a white dwarf made of carbon and oxygen. Unlike hydrogen or helium, when carbon in a degenerate white dwarf core ignites, the burning doesn't gently expand the star to regulate the temperature, because the white dwarf's pressure is supported by quantum degeneracy rather than thermal pressure. An increase in temperature doesn't lead to expansion and cooling. The result is a runaway thermonuclear reaction, consuming the entire white dwarf within seconds. The white dwarf detonates completely in one of the most brilliant pyrotechnics the cosmos offers, a Type Ia supernova. In a Type Ia supernova, a tiny Earth-sized object, the white dwarf, is obliterated, unleashing a titanic amount of energy and forging elements like iron, nickel, and cobalt in vast quantities. There is no compact remnant left, no neutron star or black hole remains, because the entire white dwarf is now an expanding cloud of glowing debris. Type Ia supernovae shine with such consistent peak luminosity, about 5 billion times the luminosity of the Sun, that astronomers use them as standard candles to measure distances across the universe. They are cosmologically important. Observations of distant Type Ia supernovae revealed the accelerating expansion of the universe, attributed to dark energy. But on a personal level, they are another way that stars die with a creative flourish. They spread iron and other intermediate weight elements far and wide, elements that may not be as abundant in core collapse supernovae of massive stars. So in binary systems with white dwarfs, we have a spectrum, from gentle novae to total annihilation in Type Ia supernovae, depending on how much mass the white dwarf steals and how quickly. Now consider binaries where both stars are massive enough to form neutron stars or black holes. There are binary systems where one star explodes as a supernova and becomes a neutron star, but the two remain bound, or become bound again if the kick isn't too strong. Eventually, the second star also goes supernova, possibly leaving two neutron stars orbiting each other, or a neutron star and a black hole, or two black holes. These pairs of dense remnants are essentially ticking time bombs. They spiral toward each other over very long periods as they radiate gravitational waves, ripples in space-time that carry energy away from the orbit. When two neutron stars finally collide, the event is cataclysmic on a different level. Picture two city-sized, insanely dense objects whipping around each other hundreds of times per second as they draw closer. In their last moments, they approach nearly a significant fraction of light speed. When they merge, enormous gravitational and nuclear forces come into play. The merged object can promptly collapse into a black hole, or, if enough support exists briefly, form a hypermassive neutron star for a short time before that too collapses. In the process, a huge mass of neutron-rich material gets flung out into space from the violently merging stars. This debris, rich in heavy elements, heats up and produces an ephemeral but brilliant glow known as a kilonova, so called because it's roughly 1,000 times brighter than a typical nova, though still dimmer than a supernova. The kilonova initially shines blue-hot from freshly synthesized radioactive elements. Then, as those nuclei decay, the glow becomes redder over days and weeks. It was by observing the light from such a kilonova, accompanying a gravitational wave event in 2017, that scientists confirmed that neutron star mergers manufacture heavy elements like gold, platinum, and rare earth elements in significant quantities. The very gold in jewelry here on Earth likely came from such an event in our galaxy's past. The neutron star merger also emits a burst of high-energy gamma rays, a short gamma ray burst, especially if jets form during the collision. These gamma ray bursts are some of the most luminous events in the universe, though very brief, lasting less than 2 seconds for the short variety, longer for collapsor-related bursts. If instead two black holes collide, imagine two invisible dark spheres merging, they release a purely gravitational scream, a burst of gravitational waves, as the only directly observable output. This was what LIGO detected in 2015. The final moments of two black holes merging, converting a few solar masses worth of energy into vibrations of space-time that stretched and squeezed the detectors on Earth ever so faintly. Such events were predicted by Einstein's general relativity and are now observed. They too are endpoints of binary evolution, two stellar mass black holes in a death spiral. There are other exotic binary interactions. A neutron star and a black hole could merge, likely gobbling the neutron star and producing gravitational waves and maybe a faint gamma burst. A neutron star and a white dwarf could collide under rare circumstances, or a black hole could slowly consume a white dwarf or neutron star, tidally shredding it. These scenarios are less commonly observed, but are theoretically possible in dense environments like star clusters. One more comparatively common binary death process. Classical novae we already discussed involve a white dwarf, but there's also a kind of middle ground event called a red nova, or luminous red nova, which occurs when two normal stars merge. While not as energetic as a supernova, it's a stellar death of sorts. The two stars cease to exist as individuals and become one star. These events can produce a significant outburst, as seen in objects like V1909 Scorpii or others, where contact binary stars spiraled together. The result is a single larger star, often shrouded in dust, and the process may eject a significant amount of the star's mass. It's a death in the sense that two separate stellar lives ended and a new one began. In all these binary cases, what's striking is how the presence of a partner star alters the outcome. A star alone might quietly become a white dwarf and sit there forever, but with a companion, it might reignite and explode. Two neutron stars alone drift through space. Together, they can create one of the most important sources of heavy elements and brilliant fireworks. From the gentle recurring nova that might just create some exotic isotopes and pretty displays, to the awesome Type Ia supernova that serves as a cosmic yardstick and forge of iron, to the mind-bending mergers of neutron stars and black holes that literally shake the fabric of space-time, binary interactions significantly enrich the tapestry of stellar death. They show that even in death, stars are not solitary actors. They can affect one another, sometimes saving their grandest drama for when they are together. Up to now, we have been describing what happens to stars and their remnants more or less from a theoretical perspective. But how do we know all this? Much of the science of stellar evolution and death has been pieced together by observing countless stars at different stages and by physics calculations that have been tested in various conditions. Still, one might wonder, no human has watched a star go through its entire life cycle. It takes millions to billions of years. So how can we be confident in this story? The answer lies in the incredible detective work of astronomy, using both light and other cosmic messengers to understand these processes. Humans have actually observed the deaths of stars for millennia, even if they didn't know what they were seeing. Ancient peoples recorded sudden appearances of bright stars that weren't there before, what we now recognize as supernovae or novae. They regarded them with wonder, sometimes as omens or messages from the heavens. For instance, in July of 1054, observers in East Asia noted a guest star near the star Zeta Tauri. It stayed visible in daylight for weeks. Today, we see the remains of that event as the Crab Nebula in Taurus. Inside it, a pulsar spins, the neutron star left from that massive supernova. In 1604, sky watchers, including the astronomer Johannes Kepler, observed a new star in the constellation Ophiuchus, Kepler's supernova, the most recent known supernova in our Milky Way. These historical accounts, though made without understanding the true nature of the events, are invaluable records. They tell us, for example, that supernovae can occur in our galaxy a few times per millennium. It's likely more have happened obscured by dust or mist due to being in the southern hemisphere, unobserved by Europeans or Far East observers. In modern times, we have developed an arsenal of instruments that allow us to catch stellar death in action across the universe. Telescopes and detectors now cover the electromagnetic spectrum from radio waves to gamma rays, and even beyond electromagnetic signals. We have neutrino observatories and gravitational wave detectors. When a massive star explodes in a galaxy millions of light years away, our optical telescopes see a pinpoint of light that wasn't there before. Robotic telescope surveys scan the sky nightly and automatically flag such new points of light or unusually brightening points. Professional and amateur astronomers then train their telescopes on them to gather more data. By splitting the light with a spectrograph, we see telltale fingerprints of certain elements, perhaps silicon and sulfur lines expanding at high speed, indicating a type Ia supernova, or hydrogen lines indicating a type 2, core collapse, supernova. The light curve, the way brightness changes over time, provides clues. A type Ia supernova has a characteristic rise and gradual fall. A massive star supernova might plateau, or have multiple peaks if complicated by circumstellar material. In fact, by studying many such events, astronomers have subclassified supernovae, type 2P, 2L, IN, IB, IS, etc., which correspond to different ways stars meet their end. Some shed their hydrogen envelopes first, some don't, etc. When a supernova occurs relatively nearby, say in a galaxy in our local group, we can sometimes directly see the debris after the explosion fades. The Hubble Space Telescope and ground-based telescopes have monitored supernova remnants and even the actual positions of supernova events decades later to see the shockwave expansion. For example, supernova 1987A, which occurred in a companion galaxy to our own, the Large Magellanic Cloud, a small satellite galaxy of the Milky Way, in 1987, has been observed continuously for decades. We saw a brightening as the shock hit a pre-existing ring of gas, previously expelled by the star, and we've been waiting for the possible emergence of a neutron star or pulsar within the debris. Only recently have there been hints of it. SN 1987A was a bonanza for learning. It was the closest supernova in centuries and was extensively studied across all wavelengths. Neutrinos are a novel way we confirmed our theories. Those ghostly particles from SN 1987A were actually detected in underground detectors on Earth, Kamiokande in Japan and others, a few hours before the visible light of the explosion reached us. This happened because neutrinos, which scarcely interact with matter, streamed out of the collapsing core immediately, whereas photons were trapped until the shockwave reached the surface of the star. The burst of neutrinos, just 24 of them detected, matched the predictions for a core collapse neutrino signal, providing direct evidence of what was happening deep in the star at the moment of explosion. It was a dramatic confirmation of stellar death physics. We felt the star's core collapse through neutrinos, then saw the star blow apart in light. In the past few years, gravitational wave astronomy has opened another new window. In 2015, the LIGO Observatory listened as 2 black holes merged, which was our first direct detection of gravitational waves. Then, spectacularly, in August 2017, LIGO and its European cousin Virgo detected a signal that indicated 2 neutron stars spiraling together. Within seconds, a gamma-ray burst was detected by orbiting satellites. Hours later, telescopes spotted a new transient glow in a galaxy about 130 million light-years away, the kilonova from that merger. Here we had essentially the complete story. Gravitational waves told us 2 neutron stars collided, gamma rays told us jets formed, and the kilonova's light, with spectra showing gold and other freshly made heavy elements, told us about the material ejected. It was perhaps the most observed astrophysical event in history, with dozens of telescopes joining in. This single event confirmed several theoretical ideas at once: that merging neutron stars produce short gamma-ray bursts and heavy elements. It was like witnessing the birth of elements, gold, platinum, etc., in real time. And it showed the power of combining different cosmic messengers, gravitational waves to pinpoint a cosmic death dance, and electromagnetic waves to witness its aftermath. Even black holes, which emit no light of their own, have become observable through their interactions. Aside from LIGO's detections of merging black holes, which produce only gravitational waves, we have observed stars orbiting our galaxy's central black hole over decades. These stars move in tight, fast ellipses, with one star, called S2, coming as close as 17 light-hours to the black hole, 4 times the distance of Neptune from the Sun, and whipping around at a few percent of light speed. By tracking these orbits, astronomers have confirmed the presence and mass of the central supermassive black hole. This achievement, in fact, earned the 2020 Nobel Prize in Physics. And as mentioned, we have even imaged the shadow of a black hole's event horizon for the supermassive black hole in galaxy M87, and very recently our own galaxy's center as well, by using radio telescopes spread across the globe. The image appears as a ring of light emitted by hot gas just outside the horizon, surrounding a dark area, the silhouette of the horizon itself. It's a stunning confirmation that the dark star predicted by general relativity is real. When it comes to observing stellar ghosts, pulsars have been detected by their pulses. Over 2,000 are known to date. Some pulsars are in binary systems, which allows us to test general relativity, such as the famous Hulse-Taylor pulsar, a neutron star pair that spirals inward exactly as gravitational wave emission predicts. White dwarfs have been observed in huge numbers as well, often through surveys like the Sloan Digital Sky Survey. We can even see extremely faint white dwarfs in clusters like M4, giving a hint that some are crystallizing as they cool. These observations line up with the theory that white dwarfs cool and fade over billions of years. Novae are observed fairly frequently in our galaxy. About 10 per year are seen, and many more likely occur on the far side of the galaxy hidden by dust. Each nova gives us insight into the accretion processes on white dwarfs. Some have even been observed to recur, e.g. RS Ophiuchi, which erupts about every 15 to 20 years. Supernova remnants, like the Veil Nebula or Cassiopeia A, have been mapped in detail by telescopes. In Cass A, the remnant of a supernova around 1680 AD, though oddly no one clearly recorded it at the time, astronomers have found the neutron star left behind, and they've even seen light echoes in surrounding dust that give clues to the original explosion. In X-rays, Cass A's image from Chandra shows an incredible expanding shell with different elements separated spatially. For example, iron is more interior, oxygen and magnesium more outside, consistent with our understanding of how supernova nucleosynthesis and ejection work. Our ability to simulate stellar deaths on computers has also advanced. We can now create models that, for example, follow a massive star's collapse and explosion, and see how asymmetries can give a neutron star a kick, or how mixing can produce certain light curves. These models are tuned by matching them to observations, say, the light curve of SN 1987A, or the spectra of various supernovae. While some details are still being researched, like the precise mechanism that makes every core collapse supernova explode rather than implode entirely, neutrinos are key, but it's a complex hydrodynamic dance. The broad strokes are strongly supported by data. Thus, through a combination of direct observation across all wavelengths, and now beyond light, historical evidence, laboratory physics, and computational modeling, we've assembled the story of stellar life and death. Each new technological leap, from Galileo's first telescope to spectroscopy, to space telescopes above our atmosphere, to neutrino detectors, to gravitational wave observatories, has added a piece to the puzzle or confirmed a chapter of the tale. We no longer merely speculate about star death, we witness it. We have seen the X-ray glow of neutron stars feeding, the gentle wink of novae, the sky-filling blast of supernovae, the faint whisper of colliding black holes. Even now, somewhere in the universe, a star is living out its final moments. Perhaps in a distant galaxy, a red supergiant's core has just collapsed, neutrinos streaming out, a shockwave on the way. Within the next few hours or days, light from that explosion will start its journey across space. In a few years, maybe it will arrive at Earth, and robotic telescopes will catch a new star in their images. Alerts will go out, astronomers will turn their instruments to study it, and humanity will collectively witness another star's death in as close to real time as nature allows. With every such observation, our understanding deepens. We are, in a sense, collecting the final words of stars, listening to their swan songs, and learning from them. One day, we will face a very personal case of stellar death, that of our own sun. But fortunately, that is far in the future. Our sun is currently a healthy middle-aged star, shining steadily and nurturing a rich biosphere on the third planet from its warmth. Yet, like all stars, it must eventually exhaust its fuel and transform. What will that look like? And what will become of the Earth? Our sun is about 4.6 billion years old. It's roughly halfway through its main sequence lifetime. For the next few billion years, it will continue to fuse hydrogen into helium in its core, gradually getting hotter and slightly more luminous as the helium ash accumulates. In fact, the sun's brightness has increased by about 10% since it formed. In another billion years or so, that slow increase will make Earth significantly warmer, potentially too warm for complex life long before the dramatic red giant phase arrives. By around 5 billion years from now, the sun will have run out of core hydrogen. At that time, it will begin the transition into a red giant. The sun's core will contract and heat, just as we described earlier, and hydrogen fusion will ignite in a shell around the core, causing the sun's outer layers to expand tremendously. It's estimated that at its largest, the sun's radius will extend to somewhere around Earth's orbit. Perhaps a little less, perhaps a little more. The exact calculations are complex and depend on how much mass the sun loses as a red giant. Mercury and Venus will almost certainly be engulfed and vaporized. Earth's fate is uncertain. Some models suggest Earth will be swallowed by the sun's expanded atmosphere, dragged inward by tidal interactions, and incinerated. Other models suggest Earth might just barely survive, orbiting within the sun's outermost tenuous layers, or just outside them after orbital expansion due to the sun's mass loss. Either way, the Earth's surface will be sterile. Long before the sun actually touches Earth, the increasing heat will have boiled away the oceans and stripped the atmosphere. The crust will glow red hot. For a while, Earth might resemble a desiccated rock, like Mercury, under the gigantic red orb of the sun filling the sky. By the time the sun is at its largest, even the outer planets will experience vastly increased solar heat. Mars might briefly enjoy Earth-like temperatures, though bathed in red light, but not for long. If any humans, or our far future descendants, are still around by then, they would have had to leave Earth, and perhaps the solar system entirely. Maybe they would take refuge in the outer reaches, on moons of Jupiter or Saturn, which might become temperate for a short period. Or more likely, humanity would undertake voyages to other star systems long before that. It's poignant to imagine that far future observers, perhaps the distant descendants of humanity or some other species that by then knows this story, could watch from a safe distance as the sun goes through its death throes. They might see the sun's color turn from yellow-white to orange to deep red as it expands. They would know, as they watch, that this was once the star that sustained the cradle of human civilization. The emotions such observers might feel blend sorrow at the loss of the sun's former life-giving form and awe at the grandeur of the transformation. As the sun's core continues to contract, it will eventually ignite helium fusion in a flash, as described earlier. The sun will shrink slightly and settle into a stable helium-burning phase for a time, becoming perhaps a bit less distended. It might then expand again for an asymptotic giant branch phase after helium is exhausted, undergoing some thermal pulsations, each expelling more of its outer layers. Finally, the sun will shed its outer envelope. The dying sun will create a planetary nebula, perhaps a glowing shell of ionized gas expanding outward, beautiful in its complexity. Some models suggest the sun's planetary nebula might be relatively faint, because the sun is not as massive as the stars that make the showiest nebulae. But it will still be a sight to behold, a ring or bubble of color, marking where our star says farewell. At the center of that nebula will lie the sun's core, a fresh white dwarf. It will likely be composed of carbon and oxygen, about half the sun's present mass, compressed into roughly Earth's volume. It will be extremely hot, well over 100,000 degrees Celsius at the surface initially. It will cool slowly over billions of years. Once the surrounding nebula drifts away into space, the white dwarf sun will remain, a small, dense, gradually cooling sphere. It will shine mostly in the ultraviolet initially, with perhaps a bluish-white hue if one could see it up close, then fade through the colors to red and eventually to darkness over trillions of years. The solar system, as we know it, will not survive this process intact. The inner planets will be gone or altered beyond recognition. The gas giants might migrate outward as the sun loses mass, since the gravitational hold will weaken. The icy bodies of the outer solar system, Kuiper belt objects, Oort cloud comets, will largely drift away or get perturbed by the changing gravity. The final configuration might be a white dwarf with a few distant cold planets, perhaps Jupiter, Saturn, Uranus, Neptune, if they aren't lost, now wandering farther out, perhaps some moons or dwarf planets, frozen solid. Over enormous timescales, even those remaining planets might detach or be perturbed by passing stars. It is a sobering scenario, the demise of our warm and life-sustaining sun. Yet, it is also strangely uplifting to know that the sun's materials will not be lost. The planetary nebula cast off by the dying sun will carry atoms that once made up our world out into the galaxy. Perhaps some of those atoms will eventually find their way into new star-forming clouds. In that sense, a piece of Earth and a piece of us will journey on, joining the great cycle of cosmic recycling. In fact, there is a theory that a supernova may have helped trigger the formation of our solar system over 4.6 billion years ago, based on certain isotopes found in meteorites that are byproducts of supernova nucleosynthesis. If true, then a star's death begot the sun's birth. And now we see that the sun's death will return the favor by contributing its matter to future generations of stars. The cosmic cycle continues. Now let's journey unimaginably far into the future of the universe, beyond not just the death of individual stars, but to the era when perhaps all stars have died. What happens after the age of starlight? The universe is about 13.8 billion years old. We live in what astronomers call the stelliferous era, age of stars, when galaxies gleam with billions of active stars. But stars consume fuel. Galaxies have a limited gas supply, and over time, star formation will slow. Astronomers project that star formation will continue on a declining curve for many trillions of years, gradually winding down as gas gets locked into long-lived dwarf stars or compact remnants. The smallest, most long-lived stars, red dwarfs, burn their fuel so slowly they can shine for trillions of years. So there will be stars twinkling for a very long time yet. But eventually, even those miserly red dwarfs will exhaust their hydrogen and turn into inert helium white dwarfs. Let's sketch the timeline. In about 100 billion years, the expansion of the universe, driven by dark energy, will likely have pulled all but our local group of galaxies beyond the observable horizon. Future beings in our galaxy at that time might think the Milky Way is the entire universe, as distant galaxies' light will have redshifted into oblivion. But stars will still be shining in our galaxy then. Fast forward to, say, 1,010,012 years from now. By this time, most stars larger than red dwarfs will have long since died. New star formation will be a trickle. Much of the interstellar medium will have been either locked in remnants or swept out of galaxies. Some star formation might still occur from collisions of brown dwarfs, or stellar remnants occasionally merging and sparking new stars briefly, but on the whole, galaxies will be dimmer. Red dwarfs, whose lifetimes can reach into the trillions of years, will dominate the starlight. They will be faint red glowworms where once splendid suns like ours shone. At around 10 trillion, 10,013 years, star formation will essentially cease. The reserve of gas for making new stars will be effectively depleted or too spread out. The universe's expansion will have put far-flung raw material beyond reach. The existing stars will run out of fuel one by one. the last truly luminous star might be a red dwarf finally flickering out. Imagine that far future night sky from some hypothetical planet around one of those last stars, if planets still exist, where once the sky was full of stars, now perhaps only a few faint red points pierce the darkness. Maybe globular clusters remain as isolated pockets of stars, slowly losing members to the galactic halo. The Milky Way, or whatever merged galaxy exists by then, our Milky Way might merge with Andromeda and others to form a large elliptical over billions of years. We'll no longer have the majestic spiral arms lit by young stars. It might be a huge ball of dark mass with occasional pinpricks of degenerate matter. When the last active star, likely a tiny red dwarf, finally exhausts its hydrogen, perhaps after 10, 14, or 10, 15 years, 100 trillion to a quadrillion years, it will expand into a small red giant, shed a bit of mass, then fade to a white dwarf. At that point, the degenerate era begins in full. The universe will be populated only by stellar remnants, white dwarfs, many of them cooled to become black dwarfs by then, neutron stars, and black holes, along with unbound planets, brown dwarfs, failed stars, and cold gas and dust. The average temperature of the universe will be dropping as well, as the background radiation is stretched to extremely low energies by expansion. What is life like in such an era? It's speculative whether life could find ways to survive around, say, a warm white dwarf, or on residual heat of a cooling neutron star, or by feeding off rotational energy of pulsars. Some scientists have pondered civilizations around white dwarfs, or even artificial habitats, feeding off black hole accretion disks, since black holes could theoretically provide energy via Hawking radiation or other mechanisms over extremely long timeframes. If any form of intelligence endures into these times, it would face ever-declining energy supplies. Time stretches on. White dwarfs gradually cool toward the background temperature, which itself might approach near absolute zero if dark energy leads to a de-Sitter space. On timescales of 10^-19 to 10^-20 years, most of the remaining planets will have either spiraled into their remnants due to gravitational radiation or interactions, or been flung out by gravitational encounters. The galaxy's shape will disperse as gravitational interactions over eons cause stars and remnants to scatter, some being ejected into intergalactic space, others falling into the central black holes. Around 10^-20 years, 100 quintillion years, the Earth, if somehow it survived as a charred ember around the white dwarf sun, would either have been absorbed by the sun's white dwarf due to orbital decay from emitting gravitational waves, though that timescale is way longer than that for Earth-Sun, or more likely, the sun's white dwarf might have cooled to, say, a few thousand K, glowing faintly red. By 1025 years, definitely, any white dwarf like the sun's will be essentially a black dwarf, radiating at almost the same temperature as the cosmic microwave background, which itself would be incredibly cold then. To any remaining observer, these once stars would be effectively invisible unless you literally bumped into one. Over extremely long timescales, quantum effects might come into play. If protons are unstable, some theories predict a proton's half-life of 1034 years, then given enough time, all the atomic nuclei in white dwarfs, planets, etc., would eventually decay into lighter particles, like positrons and gamma rays. A white dwarf could slowly evaporate into a cloud of electrons, positrons, and radiation. If protons don't decay, another process can still thin out matter. Quantum tunneling could cause the iron in black dwarfs to fuse, or the object to collapse on unimaginably long timescales, 10 or 1500 years or more, or cause it to crystallize fully and just sit. One thing that will definitely happen in the far, far future is the slow evaporation of black holes via Hawking radiation. Black holes aren't completely eternal. Quantum mechanics suggests they emit a very faint trickle of particles and radiation, losing mass in the process. For a stellar mass black hole, the evaporation time is stupendously large, around 10^67 to 10^100 years, depending on mass. For the supermassive black holes, it's even larger, on the order of 10^100 years or more. But given enough time, even these leviathans will evaporate, each ending its life in a final burst of Hawking radiation that might briefly be as energetic as a small explosion. After that, nothing of them remains. As we approach times like 10^100 years and beyond, the universe becomes very quiet and sparse. All galaxies have dissipated. All black holes are gone. The particles left are mostly subatomic: electrons, positrons, neutrinos, and extremely low-energy photons, stretched out to absurdly long wavelengths. The expansion may eventually dilute even those, so that on average, you might have to search a volume larger than the observable universe today to find a single particle. The temperature of the universe will asymptotically approach absolute zero. This is the heat death of the universe, sometimes called the Big Freeze. It's a dark picture, endless space with virtually nothing in it. No starlight, no planets, no warmth, just the feeble afterglow of a cosmos that once blazed with galaxies. If consciousness or life hasn't found some way to circumvent the need for conventional energy, it would have long since flickered out by this stage. This is the ultimate endpoint of all the individual star deaths we've discussed. Everything ends, even the cosmos as we know it. Unless, perhaps this isn't truly the end. Some speculative ideas suggest that given inconceivably long times, random quantum fluctuations could produce a new Big Bang or a Boltzmann brain, a self-aware configuration of particles popping up by chance, though the time frame for that is mind-boggling. Other theories propose that our universe might tunnel into a lower energy vacuum state, essentially triggering a new kind of Big Bang that restarts things, though that would obliterate the current universe in the process. These ideas are currently beyond verification and wander into the realm of metaphysics or highly theoretical physics. For all practical purposes, under known physics, once the last black hole evaporates, the universe will be effectively dead for eternity, an ever-expanding, nearly empty darkness where nothing of note happens. This future is almost impossibly far away. It makes the lifespan of even the longest-lived star seem like a blink, yet thinking about it can evoke a deep sense of existential awe. The universe had a beginning, and it may have an end. We live in a chapter, the chapter of shining stars and bright galaxies, that will not last forever. But it is our chapter, rich with story and meaning. Through this long exploration, a theme has quietly taken shape. In the cosmos, every death is also a form of creation. A star's death creates the chemical elements that may seed life. The remnants of stars lead to new phenomena, pulsars, black holes, that enrich the fabric of reality with their strange properties. Even the eventual fade of the universe sets the stage for who knows what, perhaps a rebirth, perhaps a final piece. Philosophically, the story of stellar death resonates with us because it mirrors aspects of our own existence. We are born, we shine with life, we use up our days, and eventually we must go. But we are part of cycles larger than ourselves, biological cycles, cultural cycles, and indeed cosmic cycles. There is an ancient intuition in many mythologies that destruction and creation are two sides of a coin. From the ashes of the phoenix, a new phoenix arises. In Hindu mythology, the dance of Shiva destroys so that Brahma may create anew. The ancient Egyptians saw the sun die each dusk and be reborn at dawn. In the cosmic perspective, these poetic insights are quite literally reflected in the behavior of stars. A massive star perishes in a supernova, and from its remnants, new stars and planets will one day form. There's a continuity, an immortality of sorts, not for the individual star, but for the patterns and materials of which it was made. For most of human history, the stars were thought of as eternal and unchanging. the realm of the gods, or the perfect and divine, in contrast to the mortal, mutable earth. Learning that stars are born and die has been a profound shift. It has united the heavens and the earth into a single tapestry of nature. The calcium in our bones and the iron in our blood are proof that we and the stars are intimately connected. The life cycle of a star is not fundamentally different from the life cycle of a flower in a field. There's a sprouting, formation, a bloom, main sequence, a withering, giant phase, and a scattering of seeds, nebula and remnants, to ensure the next generation. It's just on a much grander stage and longer timeline, but the pattern is familiar. We see it in our own lives and in the ecosystem around us. What meaning can one take from this cosmic perspective? Some might find it nihilistic. Everything ends, even starlight dies, and in the far end, nothing remains. But one can also find it deeply inspiring. Death in the universe is not a permanent annihilation. It's transformation. The end of one thing is the beginning of another. The universe wastes nothing, rearranging dead stars into new stars, dead galaxies into new galaxies, on larger scales through collisions, perhaps dead universes into new universes if some theories hold weight. If even the stars, those eternal lights in the sky, must die, then how remarkable it is that out of their death comes something as poignant and wonderful as us, beings made of their dust, able to contemplate the very process that gave us form.
There is also a lesson in humility and gratitude. We gaze at the stars often with a sense of permanence. They seem the fixed backdrop of our lives, but they are on their own journeys from birth to death. We happen to live in a cosmic age rich with stars. It will not always be so. This recognition makes a clear night sky even more cherishable. We are witnessing a phase of the cosmos that, however long, is transient. We are fortunate to see a universe awash in light. The darkness that will come is beyond our personal timescales, but its inevitability makes the present cosmos no less splendid, if anything, more. Above all, the death of stars teaches us that endings can be creative. The stars do not simply vanish, they leave behind gifts. They forge the gold in our rings, the oxygen in our lungs, the silicon in the rocks beneath our feet. They leave behind neutron stars that keep time better than atomic clocks, and black holes that test the limits of physics. Even in their violent final acts, there is a profound generosity. They give themselves to the universe. We too are of star stuff and will return our atoms to the greater pool. In a poetic sense, one could think, as we live, we are a way for the universe to know itself, since our brains are made of those very atoms forged in stars and now contemplating the cosmos. In dying, we give those atoms back so that new forms, new consciousness can one day arise. It's a scientific truth that every atom in our body will outlast us, moving on to become parts of other organisms, the air, the ocean, and over geological time, part of new minerals, or maybe subducted into Earth's mantle, or blown out to space if Earth loses some atmosphere. On very long timescales, perhaps our atoms will cycle through new planets, or even be lofted off Earth when the sun dies. It's a kind of immortality, material, not personal, but comforting in its continuity. As we near the conclusion of our journey, step back and look at the night sky again, perhaps in your imagination if it's not visible right now. See the stars twinkling. Look up at the night sky and breathe in. Feel the air enter your lungs. That air contains oxygen that was created in a red giant star billions of years ago. It contains nitrogen that may have been produced in some long ago stellar factory, carbon from another. The iron in your blood was born in a supernova explosion, traveling through space, eventually finding its way into the cloud that made the sun and planets, and then into your body. Every breath is a connection to that stellar heritage. As you exhale, perhaps some of those atoms will return to the atmosphere,
and a plant will take them in tomorrow, incorporating the carbon into a leaf. Years from now, that carbon might be part of a fruit eaten by another person and become part of their body. And so the cycle goes on Earth, small echoes of the greater cycle of stars. We are all connected through these cycles. When we gaze at a distant star, we are seeing it often across a great span of time. The light reaching our eyes might have left that star hundreds or thousands of years ago, before the rise and fall of nations, before any living human. In that sense, to look at the stars is to look into the past. We are literally witnessing ancient history. Some of those pinpoints of light are from stars that have already died, their light only now arriving. The cosmos is a memory machine, preserving in the speed of light the images of the past. The night sky could be seen as a grand memorial of stars, some alive, some long gone, but all appearing together to us as if coexistent. We remember the stars by their light, and in turn, we carry the stars' memory within us because we are made of their remnants. The universe has enabled us, beings of matter, to evolve and eventually understand this very fact. Through our studies and stories, the cosmos is remembering itself. Our knowledge of stellar evolution is the universe's self-reflection. We, tiny, ephemeral humans, have figured out how stars live and die. We've collected the whispers of ancient light and decoded the messages of neutrinos and gravitational waves to fill in pages of the cosmic story. In so doing, we are giving voice to the stars that cannot speak for themselves. We are eulogizing them even as we celebrate their role in giving us life. When you next find yourself under a clear, starry sky, take a moment to feel the depth of time and the cycles at play. That band of the Milky Way is the combined glow of billions of stars at various stages, some just being born in nebulae, some shining in middle age like the sun, some swelling into red giants, some already collapsed into remnants hidden in the mix. Perhaps one of those stars will explode tomorrow and be seen by us in a few thousand years, given distance. Perhaps around one of those stars, new civilizations will one day come to be, using the elements those stars provide. We are not separate from this grand cosmic web. We emerged from it. We return to it. There is a profound kinship in knowing that the carbon in your cells was forged in stellar hearts. It binds us to the universe, to the stars that died so that we might live. This knowledge can influence how we see our own lives and deaths, not as isolated events, but as continuing contributions to an ongoing story. Just as a star's death enriches the galaxy, maybe the mark we leave, through our actions, creations, and children, or at least the literal atoms of our body, enriches the tapestry of humanity and life. And so, the death of stars is at once an end and a beginning, destruction and creation fused in one cosmic act. It is a beautiful paradox that the universe appears to operate. Nothing lasts forever, yet nothing is ever truly lost. The atoms always cycle through new forms. The energy finds new channels. Even black holes, which hoard matter and energy, eventually give it back when they evaporate. This journey has been long and filled with wonders, from the quiet death of a sun-like star casting a glowing nebula, to the explosive demise of a supergiant birthing neutron stars and black holes, to the mergers that ripple space-time, to the ultimate fate of a cosmos drifting into darkness. Throughout, we find echoes of our own existence, and perhaps guidance for our own lives. We learn that great energy and growth, like a star's main sequence, eventually yield to change and aging, the giant phase, and finally to transition, death. But we also learn that what comes after can be meaningful. A star becomes a white dwarf that may one day spark a nova and bring new light. Our lives might influence generations ahead in ways we cannot imagine. Under the eternal night, we contemplate these things. The stars do not last forever, but their story does, written in us and around us. In the endless night, we remember the stars, and through us, the stars remember themselves. In the silent emptiness of space, a star dies. One moment it shines as a distant pinprick in the darkness. The next, it erupts in a soundless flash of light that briefly outshines an entire galaxy. A titanic explosion unfurls in utter silence. No roar, no crash, for in the vacuum of space, there is no medium for sound. It is a cosmic firestorm seen across light years, a brilliant beacon of death that appears without warning and vanishes just as quickly. For a few fleeting weeks, this single dying star pours out more light than billions of suns, blazing so brightly that if we were watching from a nearby world, it would paint shadows on the ground and outshine the night's full moon. Yet there is only silence. The star's final scream is in light, not sound. An immense outpouring of energy racing outward through the dark, telling anyone who cares to look that a star's long life has ended in cataclysm. What are we to feel, witnessing such a violent cosmic death? There is terror in the idea. A star, an object of almost eternal constancy in our sky, can explode without mercy. But there is also awe. In that silent explosion, we sense power beyond comprehension. The death throes of a sun many times larger than our own, unleashing energy in a few seconds that our sun will not emit in 10 billion years. Here is a celestial paradox, an event at once beautiful and destructive. A supernova, as astronomers call it, is the most brilliant of stellar fireworks. An eruption of light so powerful it can be seen across the universe. It is nature's way of shouting across the cosmos, a final cry of a dying star that echoes in starlight rather than sound. We watch in reverence, hearts humbled, for this silent, stellar eruption is more than just an ending. It is a moment of cosmic rebirth, a paradoxical creation forged by destruction.
The universe we will find is full of such paradoxes.
But how can a star, a colossal ball of plasma that has shone for millions of years, simply explode? What chain of events leads to this soundless flash in the sky? To answer these questions, we must journey into the heart of that star, into the forces and fires that sustain it, and ultimately into the tragedy that ends its life. Only then can we understand why this cosmic violence is not an empty tragedy, but a necessary drama that creates new worlds and even life. So let us venture now into the story of a star's life and death, a story written in the language of astrophysics and nuclear fire, yet rich with poetic grandeur, the story of a supernova. Imagine a star many times more massive than the Sun, born in a nebula of gas and dust. For eons, it has burned brightly, converting simple elements into heavier ones in a relentless alchemy. In its core, hydrogen, the simplest of all elements, fuses into helium, releasing the energy that makes the star shine. This process of fusion is the star's lifeblood, a delicate balance between pressure and gravity. Deep in the core, the outward push from fusion generated heat fights against the inward crush of gravity. As long as there is fuel to burn, the star maintains this equilibrium, shining steadily in the firmament. But stars, like living things, have cycles. Our massive star eventually exhausts the hydrogen in its core after millions of years of brilliant stability. Gravity, ever patient, begins to gain the upper hand. The core contracts and heats up until a new fusion fire ignites. Now, helium fuses into carbon and oxygen. The star has entered old age, swelling into a bloated giant. If we could see it up close, we would find its appearance transformed, often into a red supergiant, a star swollen to hundreds of times its original size. Its outer layers cooled and ruddy. Inside, however, the core burns hotter and hotter as it fuses heavier elements in turn. Shells of fusion surround the core like the layers of an onion, each shell burning a different element. Closest to the center, carbon fuses into neon. In a shell above, neon burns to magnesium and oxygen. Above that, oxygen fuses into silicon. Each stage produces the fuel for the next, and each stage of fusion burns faster than the last. What once took millions of years, burning hydrogen, gives way to shorter phases. Helium burning lasts a fraction of that time, carbon burning perhaps only centuries, oxygen mere months, and finally silicon burning might last only days. The star is living on borrowed time, rushing through its life's finale at breakneck speed. Layer by layer, like a great cosmic onion, the star builds up a core of iron deep in its center. Iron. This is a fateful element in the life of a massive star. For all the previous fusible fuels, hydrogen into helium, helium into carbon, and so on, fusion released energy. This energy held up the star's weight, staving off gravity. But when fusion creates iron, the game changes. Fusing iron does not release energy, it consumes it. The atomic nucleus of iron is the most tightly bound of all common elements. You cannot fuse iron into something heavier without paying an energy price. And so, as iron accumulates in the core, the star is unknowingly building a bomb at its center, a gravitational time bomb. With no more energy to be gained from fusion, there is no outward pressure that can be won from turning iron into heavier elements. The stellar core, once a powerhouse of light, becomes a dead weight of iron atoms. In the star's final moments, the iron core grows to a critical mass. Imagine a sphere of iron as large as Earth, but containing nearly the mass of our Sun, buried at the center of a star hundreds of millions of kilometers across. This core is supported only by the desperate pressure of electrons jostling in the iron nuclei, a quantum pressure, holding collapse at bay like an overloaded spring. But as the iron core's mass approaches a limit E, even this exotic electron pressure cannot hold back gravity. The core has run out of road. In a fraction of a second, it collapses. Gravity slams the core inward with incredible force, and nothing in nature can stop it. At the center of the star, densities soar and temperatures spike to billions of degrees. Iron nuclei disintegrate. High-energy photons smash iron atoms into fragments of helium, protons, and neutrons in a process called photodisintegration. Electrons are forced into protons, turning them into neutrons and releasing a flood of neutrinos. The core, in effect, is utterly breaking down, and in the span of a heartbeat, it implodes from a sphere the size of a city to an ultra-dense ball of neutrons only a few kilometers across. Gravity has won. The core is now a neutron star, an object so dense that 1 teaspoon of its material would weigh billions of tons on Earth. If the star is extremely massive, the core's collapse may not stop even there. It can continue into an infinitesimal point, a newborn black hole. For an outside observer, this moment is invisible. It happens hidden in the star's interior, but its consequences are about to burst forth. As the core collapses, it reaches fantastical densities, even comparable to an atomic nucleus. At that point, the collapse rebounds. The core's inner region stiffens abruptly, and the infalling material crashes against this hard stop. The result is a shockwave that begins to travel outward. Think of it like a sudden jolt. The core, having imploded, bounces slightly and sends a powerful pressure wave racing up through the star's layers. Yet even this might not be enough to blow the star apart. The shockwave expends tremendous energy, ripping apart iron nuclei in its path, and it can stall within the star as it encounters the overlying heavy layers. Here, the ghostly heroes of our story emerge, neutrinos. These nearly massless, elusive particles were released in staggering numbers during core collapse. A flood of them pours out of the core, carrying away the energy of gravity's triumph. In fact, 99% of the energy of the collapse is released as neutrinos, an almost inconceivable torrent of invisible particles. Under normal circumstances, neutrinos hardly interact with matter at all, but the sheer intensity of the neutrino blast from the collapsing core is unprecedented. In that brief moment, the core shines with neutrinos more powerfully than 1 billion suns shine with light. As the shockwave stalls, these neutrinos streaming outward deposit a fraction of their energy into the star's layers, rejuvenating the shock. It's as if an army of ghosts all struck in unison, delivering a final push to blow the star apart. A deafening silent roar in neutrinos propels the shockwave outward again. Within milliseconds, the core has transformed from a quiet iron ball into an engine firing out neutrinos and launching a shock front through the star. Now the doomed star's outer layers finally feel the effects. A ferocious blast wave races outward from the core, ploughing through each overlying shell of elements. The star's immense envelope, hydrogen, helium, carbon, oxygen, all the layered elements built up over its life, is violently ejected. The shock heats the stellar material to incandescent temperatures, so as it blows out to space, it begins to glow brilliantly. The star is literally tearing itself apart from the inside. Within hours, the shock reaches the star's surface. The once stable star has become an expanding fireball. To any distant onlooker, this is the moment the star suddenly brightens by orders of magnitude, announcing the supernova. The dying star, which may have been a modest point of light before, now becomes something like a miniature galaxy in appearance, a single point shining with the luminosity of billions of suns. For a brief time, this one star's explosion can rival the brightness of an entire Milky Way of stars. Imagine it, a pinpoint of light in the sky outshining every other star in its galaxy, pouring out energy at an impossible rate. In one supernova, more energy can be released than our sun will radiate over its entire 10 billion year lifetime. The numbers defy imagination. The exploding star's luminosity can reach tens of billions of times the sun's output. Seen from a nearby planet, the night would turn into day for weeks. Even from thousands of light years away, such a supernova might be visible with the naked eye, as has happened at a few points in human history when supernovae in our galactic neighborhood briefly appeared as new stars in the sky. The Chinese, over 2 millennia ago, recorded a mysterious guest star that shone for months where no star had been before. Medieval astronomers, too, were astonished by sudden stars that could even be seen in daylight. All of these were supernovae, the spectacular deaths of distant suns, flaring into visibility across the void. In these moments of peak brilliance, the supernova is a mesmerizing sight. The star's outer layers hurtle into space at thousands of kilometers per second. A spherical tsunami of gas racing outward. The material glows from the immense heat of the explosion, producing an expanding shell of radiance. If the star was a red supergiant before it exploded, the shock may take some time to break out, and the supernova's light will then linger with a gradual decay, sometimes showing a plateau of brightness as its expanding hydrogen-rich envelope shines. If the star was a blue supergiant, more compact and hotter, the explosion might rise and fall faster, perhaps with an initial burst of high-energy radiation. Different stars produce different light curves in their death. Some supernovae maintain peak brightness for weeks, whereas others fade more quickly. In all cases, however, the spectacle eventually wanes. The enormous blast, having expended its energy, sees its debris cloud expand, thin out, and cool. Over months, the supernova's visible light diminishes, often transitioning to a dim nebula of glowing embers. But in those first days and weeks, the radiance is unrivaled. The supernova floods the spectrum with light, from energetic X-rays and ultraviolet flashes generated at shock breakout to the optical light that we see with our eyes, and onto infrared and radio waves as the ejector plows into surrounding space. It is a multi-wavelength beacon proclaiming a star's demise. Not every star ends this way. Only those of sufficient mass die in such spectacular fashion. Stars born with more than about 8 times the Sun's mass are destined for these core collapse supernovae. Our Sun, by contrast, will never explode. Far in the future, it will swell into a red giant and then gently shed its outer layers to form a planetary nebula, leaving behind a dense ember called a white dwarf. But massive stars live fast and die young. They burn through their fuel quickly and then explode, as we have seen. The supernova we've described, the collapse of a massive star's iron core, is one major type of stellar death. Yet intriguingly, there is another very different way to trigger a supernova. Not all stellar explosions come from a single massive star collapsing. Some come from a more subtle kind of stellar doomsday, a runaway nuclear detonation on a white dwarf star. In binary star systems, 2 stars orbiting each other, it sometimes happens that one star is a white dwarf, the tiny, dense remnant of a sun-like star, and it begins stealing matter from its companion. If the white dwarf gains enough mass, it can reach a critical threshold at which the pressure and temperature in its core ignite a furious wave of nuclear fusion. In a matter of seconds, carbon and oxygen inside the white dwarf detonate in a thermonuclear blaze. The white dwarf is blown to bits in a special kind of supernova explosion. Astronomers call this a Type Ia supernova, a thermonuclear supernova, and it differs from the core collapse supernova of a massive star. There is no iron core collapse to a neutron star. Instead, a white dwarf is completely destroyed by an uncontrolled fusion reaction. This too produces a dazzling burst of light and ejects star material into space, though the mechanism is fundamentally different. Type Ia supernovas tend to have very consistent brightness because they all explode when the white dwarf hits that same critical mass. They have proved immensely useful as standard candles for measuring cosmic distances. Their predictable luminosity allows us to gauge how far away they are by how bright they appear. But beyond their utility, they are yet another dramatic path for stardust to be scattered through the galaxy. Thus, the cosmos gives us 2 grand pathways to supernova: the implosion of a massive star's core and the detonation of a dead stellar core in a binary system. In the first, a giant star dies and leaves behind a neutron star or black hole. In the second, a small degenerate star is utterly obliterated, leaving no compact remnant at all. Both types scatter the star's elements into space with explosive force. Both are extremely luminous, though the details of their light differ. Astronomers distinguish them in observations by their spectra. Core, collapse supernova show signatures of the elements in their progenitor's atmosphere, whereas Type Ia supernovae lack hydrogen and instead show strong silicon, calcium, and iron lines from the white dwarf's incinerated interior. But to the eye, all these explosions look somewhat similar. A new star, like beacon, appears, shines intensely for a time, then fades. It is only by dissecting the light with telescopes and spectra that we uncover the tale of their origin written in the starlight. Whichever the type, a supernova is far more than an ending. As the exploded star's debris billows outward, it carries a priceless cargo, newly forged elements. In the ferocious furnace of the supernova, and in the final stages of the star that led up to it, nuclei of atoms have been fused into heavier forms. All the elements, heavier than hydrogen and helium, the carbon in your cells, the oxygen in the air, the calcium in your bones, the iron in your blood, were forged in stars and unleashed by supernovae. In fact, many of the heaviest elements are created during the supernova itself, in the extreme neutron-rich environment of the explosion. When that massive star's core collapsed and then blew apart, it created conditions for a rapid fusion of nuclei, a process scientists call the R process, which can build rare heavy elements like gold, uranium, iodine, and others that normal stellar burning could not produce. The hurricane of nuclear reactions unleashed in a supernova forge an array of new atomic nuclei. Then the explosion flings these atoms out into space, seeding the galaxy with the raw material for future stars, planets, and life. Think about what this means. Every atom of oxygen you breathe, every atom of carbon in your muscles or calcium in your teeth, was cooked up in the heart of a star and scattered across space by a supernova. Without supernovae, those elements would never have found their way into new generations of star systems. Without supernovae, life would not be possible. As one NASA science summary starkly puts it, the heavy elements that make our world solid and our bodies functional, iron, calcium, carbon, nitrogen, all trace their origins to stellar furnaces and explosive deaths. A supernova is thus not merely the death of a star. It is a cosmic resurrection of its substance, dispersing enriched matter into the galaxy to become the stuff of new celestial bodies. In the aftermath of a supernova, the expanding remnants of the star mix with the interstellar medium, enriching it. Over time, this debris might cool and collect into clouds, and those clouds can collapse to form new stars and planets. Every supernova is both an end and a beginning. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were brewed in the nuclear hearts of long, dead stars and cast into the galaxy by supernova explosions. We truly are made of stardust, born from stellar death. As the supernova's gaseous remnants expand and sweep through space, they shock and compress the clouds of interstellar gas they encounter. The blast wave from one star's death can trigger the birth of others. When the shock front slams into a cold molecular cloud, it can squeeze parts of it enough to start gravitational collapse, lighting new stars like kindling sparked by a flame. In this way, supernovae participate in a grand cycle of stellar life. A massive star dies and explodes. Its remnants mix into a nebula, and that disturbance helps give birth to the next generation of stars. Generations of stars are linked across time by these explosions, each supernova enriching the galactic gas with heavier elements and stirring it up. Our own sun and planets were born from such an enriched cloud, one polluted by the ashes of countless ancient supernovae. In a very literal sense, the death of those stars made possible the birth of our solar system. The cycle of stellar life and death is evident in places like the Pillars of Creation or the Orion Nebula, where young stars shine amidst clouds seeded with heavy elements, likely kicked into motion by long ago supernova blasts. Even now, across the Milky Way, supernova shockwaves are slamming into clouds, sculpting them, sometimes triggering new stars, sometimes dispersing the gas and halting star formation in that region. Supernovae are the galaxy's great architects and janitors. They shape the environment, sweeping clean some areas, clumping material in others. They regulate the very ecology of the galaxy, ensuring that star formation does not proceed too fast or too sluggishly. Without the energy injection from supernovae, gas might collapse into stars more efficiently, exhausting galactic gas early, or conversely, without supernova-induced compression, some stars that exist today might never have formed at all. In these ways, the violence of supernovae helps maintain a balance, distributing gas and heavy elements widely and preventing any one part of a galaxy from hogging all the raw material for starbirth. After the brilliant light of a supernova fades, what remains? Often, at the center of the expanding debris, there lies a newborn neutron star, the collapsed core of the star, now an ultra-dense sphere, perhaps only a dozen kilometers across. It may be spinning rapidly and emitting beams of radiation as a pulsar. In other cases, if the original star was hefty enough, Nothing macroscopic remains at the core. The remnant core collapses all the way to a black hole, an abyss from which not even light can escape. Surrounding that central remnant, we see the supernova remnant, an expanding cloud of gas that was once the star's outer layers. The Crab Nebula is one such remnant, the tattered filamentary remains of a star that blew itself apart in the year 1054 AD. In the Crab's center, a pulsar spins, energizing the nebula with winds of particles. Over thousands of years, these remnants, like the Crab or Cassiopeia A or SN 1987A's debris, will disperse into the general interstellar medium, blending their enriched guts into the galaxy's gas. Astronomers glean a wealth of information by studying the light from supernovae and their remnants. Each element in the ejected gas produces specific spectral lines, bright or dark lines at particular colors, that act like fingerprints. By splitting the supernova's light through a spectroscope, scientists can identify which elements are present in the explosion's debris. For example, they might see lines of hydrogen, or of silicon, or oxygen, or calcium. These tell us the composition of the star's layers and the products of its nuclear burning. A supernova's spectrum changes over time as the explosion evolves. Initially, it may show signs of the hot, dense conditions. Then, as the ejector expands and cools, distinct element signatures emerge. Type Ia supernovae, for instance, are notable for a strong silicon line in their early spectrum, betraying their white dwarf origin. Type II supernovae often show hydrogen lines from their outer envelopes and later a rich soup of lines from metals synthesized in the blast. By analyzing these spectral fingerprints, we confirm that the building blocks of planets and life are synthesized in these explosions. We see freshly minted nickel decaying into iron. We see radioactive cobalt. We see oxygen, magnesium, sulfur, and more, all mixed in the stellar debris. Each supernova is like an autopsy of a star, the spectral lines revealing the star's inner secrets and the outcome of its final nuclear reactions. Beyond visible light, supernovae emit across the electromagnetic spectrum. In fact, some of the most telling signs of a supernova come in forms of light our eyes cannot see. X-rays, for example, are emitted by the supernova shock heating the surrounding gas to tens of millions of degrees. Observatories like NASA's Chandra X-ray telescope have captured the X-ray glow of supernova remnants, revealing elements via their X-ray spectral lines and showing how the shockwave propagates. Radio waves, on the other hand, arise from electrons accelerated to near light speed by the magnetic turbulence in the shock front, a process known as synchrotron radiation. Many supernova remnants, like the famous Cassiopeia A, shine brightly in radio, appearing as expanding rings or shells. By tuning into radio, astronomers map the size and expansion speed of the remnant, and even discern clumpy structures in the ejector. Infrared observations peer through dust that visible light cannot penetrate, allowing us to see newly formed dust within supernova remnants, or the light echoes reflecting from interstellar dust. Across the spectrum from gamma rays to radio, the supernova broadcasts its story. Gamma ray telescopes detect the high-energy photons from the decay of radioactive elements like nickel, 56, and cobalt, 56, forged in the explosion, direct evidence of the nuclear synthesis that occurred. In 1987, when a supernova exploded in a nearby dwarf galaxy, detectors on Earth even caught a flurry of neutrinos, those ghostly particles arriving hours before the visible light, a stunning confirmation of core collapse theory. That was the first time humans directly detected neutrinos from a supernova, proving that in those dark, silent moments deep inside the star, a huge neutrino release truly occurred. Today, neutrino observatories lie in wait for the next nearby supernova. An international network of underground detectors forms a kind of early warning system. If multiple detectors suddenly register a burst of neutrinos, astronomers know that somewhere in our galaxy, a star's core has collapsed. They will scramble to point telescopes and catch the light from the explosion as it emerges. In this way, even the nearly undetectable neutrinos serve as messengers, giving us a heads up that a star has died before we even see the flash. We have also developed all sky surveys to catch the optical flash of supernovae as early as possible. Robotic telescopes scan the heavens nightly, comparing new images to older ones, looking for the sudden appearance of a new point of light. Projects like the Young Transient Surveys have netted hundreds of supernovae, some captured just hours after explosion. With each new discovery, alerts go out across the globe so that larger telescopes can begin detailed observations immediately. The goal is to witness the opening act of a supernova, something historically rare. For most of human history, we only saw supernovae days or weeks after they ignited, when they were bright enough to notice by eye. Now, sensitive instruments can catch the very moment a supernova goes off, capturing the initial flash of the shock breaking out of the star. These early moments contain unique information. For example, a brief pulse of ultraviolet or X-ray light may reveal the radius of the star. By catching supernovae early, we peel back the curtain on the star's final preparations for death. In fact, astronomers have even managed to observe a few massive stars in the final days and weeks before they exploded, a dramatic achievement once thought nearly impossible. In one recent case, a red supergiant star was observed to brighten and shed material a couple of months before it ultimately went supernova. The star was under watch by a telescope in Hawaii during the summer of 2020. It showed unusual turbulence and became enshrouded in a cloud of gas. Then, in September of that year, it exploded as supernova SN 2020 Tetlef, and for the first time, humanity had seen the death throes of a normal massive star prior to explosion. This breakthrough observation suggests that some massive stars undergo a brief period of instability just before core collapse, perhaps ejecting some of their outer layers or experiencing a burst of nuclear burning that causes them to vomit out gas and dust. It's as if the star knew its end was coming and convulsed in its final moments. These pre-supernova outbursts might be more common than we realized, and now that we know what to look for, dedicated monitoring of known massive stars may one day catch another in the act of readying for detonation. Seeing a star alive one week and gone the next brings home the reality that these cosmic giants are not eternal. They live and die on timescales we can witness if we pay close enough attention. Even without these advance warnings, there is no doubt when a supernova has occurred. After the flash, the sky is left with a new glowing remnant that wasn't there before. Ancient peoples who saw guest stars had no way of knowing what they were. We, armed with physics, can decode the event. We might turn our telescopes to the coordinates of a new supernova and quickly pick up the signatures of certain elements, telling us if it was a massive star collapse or a white dwarf detonation. If we see hydrogen lines, we know a massive star kept its envelope, a Type II supernova from a red supergiant. If instead we see no hydrogen, but strong silicon and iron, we know a white dwarf blew itself apart. If we see helium but no hydrogen, that suggests a star that lost its hydrogen shell. No hydrogen or helium, but oxygen, neon, magnesium. That could be a Type Ike, a star that lost even more before exploding. Each kind of star death leaves a distinct fingerprint in the light. With modern instruments, deciphering these fingerprints has become almost routine, turning up stories of stars in their last phases. Some were red supergiants shedding mass, others were wolf, Rayet stars that left no trace of hydrogen in their supernova, and some, as mentioned, were white dwarfs pushed over the edge by a companion. Among the cosmic blasts we've recorded, there are some especially rare and powerful outbursts. Not all supernovae are equal. A few are exceptionally luminous, far beyond the norm. These are fittingly called superluminous supernova. Imagine a supernova 10 or even 100 times brighter than a typical core, collapse, or type Ia explosion. Such brilliance strains the known mechanisms. A normal collapse or detonation doesn't easily explain it. Astronomers suspect that in some of these cases, an additional power source is at work. One leading idea is the presence of a newly formed magnetar, a neutron star with an extremely strong magnetic field, pumping energy into the ejector. If a neutron star is born spinning extremely rapidly with a magnetic field thousands of times stronger than a typical pulsar, it can act like a dynamo. As it spins down, it transfers its rotational energy to the explosion, heating the debris and making it glow far more brightly for an extended period. Essentially, the magnetar's energy injection is like a central engine boosting the supernova's luminosity. Another possibility for superluminous events is the collision of the ejector with a dense shell of gas around the star. If the star shed a large amount of mass shortly before exploding, then when the supernova blast hits this material, it converts kinetic energy into light very efficiently, producing an extremely bright display. Some of the most luminous supernovae ever seen might be explained this way. The supernova slams into a cocoon of gas dumped by the star in the years prior, lighting it up. Yet another mechanism, applying to the most massive of stars, is the pair instability supernova, a peculiar fate where a single star so massive basically obliterates itself entirely. In those monstrous stars, the core becomes hot enough that gamma rays start converting into electron-positron pairs, suddenly reducing the radiation pressure and causing the core to contract and ignite an extremely violent thermonuclear burning that tears the star apart completely. Pair instability supernovae are theorized to be the most energetic explosions a star can undergo, even bigger than normal core collapse events. And they leave no remnant at all, just a huge cloud of newly minted heavy elements. Observations of an extraordinarily bright supernova in 2006 suggest it might have been one of these events. That star may have been on the order of 200 solar masses and literally blew itself to bits, producing an incredible brightness sustained by the decay of a large mass of radioactive nickel in its ejector. One superluminous supernova discovered in 2015 and named ASASN Illich astonished scientists by reaching a peak brightness 20 times greater than the combined light of the Milky Way's 100 billion stars. For a time, that one exploding star radiated as much energy as 570 billion suns, the brightest explosion ever reliably observed. To explain such an extreme, researchers proposed that a fast spinning magnetar might be behind it, dumping its rotational energy into the ejector and essentially supercharging the explosion. If true, that magnetar would have to be near the upper limits of what physics allows, a neutron star engine pushing the explosion to luminosities at the theoretical fringe. These rare supernovae stretch our understanding of physics. They are nature's overachievers, forcing us to consider exotic ideas like pair, instability, and magnetar engines to account for their brilliance. But they reaffirm an underlying theme. Even in death, stars can be wildly diverse in how they go. The diversity doesn't end there. Some collapsing massive stars unleash not just light, but also focused beams of energy that we observe as gamma ray bursts. Long duration gamma ray bursts, bursts of high energy gamma photons lasting a few seconds to minutes, have been linked to the deaths of very massive, rapidly rotating stars. In these cases, as the star's core collapses into a black hole, it can form a swirling disk of accreting material around the black hole. Magnetic forces in that disk can launch narrow jets of plasma at nearly the speed of light, boring through the collapsing star and punching out into space. These jets, when they finally escape the star, produce an intense flash of gamma rays, the gamma ray burst. For an observer located along the line of one of those jets, The collapsing star appears as one of the most violent events in the universe, second only perhaps to the Big Bang itself in instantaneous brilliance. Gamma-ray bursts are so luminous that we can detect them across the observable universe. They announce the birth of a black hole in the heart of an exploding star, and usually, a supernova is observed in the aftermath. These events are colloquially called hypernovae by some, essentially a supernova with a GRB, indicating an exceptionally energetic explosion with jets. Not every supernova from a massive star does this. It likely requires special conditions. But when it happens, it's the ultimate cosmic drama. A star not only blows up, but also shoots out a pair of killer beams that can fry anything in their path for dozens of light years. Fortunately, such GRB-oriented supernovae are rare and usually far from Earth. They serve to remind us that the outcome of a star's death can be multifaceted: explosion, collapse, neutron star, or black hole, and sometimes relativistic jets that carry away a huge fraction of the energy. Even within the more mundane kinds of supernovae, nuances abound. Consider the red supergiant stars. When one of these blows up as a Type 2 P supernova, it typically shows a characteristic plateau in its light curve, a period of about 100 days where the brightness remains nearly constant. This plateau is caused by the enormous hydrogen envelope that the star had. The shock heats the hydrogen, and as that extended envelope recombines from ionized to neutral, it releases a steady glow of light over weeks. On the other hand, a blue supergiant progenitor can yield a supernova with a faster rise and decline, since it lacks such a distended envelope of hydrogen. A famous example of this was the supernova observed in 1987. Its progenitor was a blue supergiant, and the light curve was quite different from a standard Type 2P, showing an initial burst and then a dip before rising again. This taught astronomers that not all massive stars explode from the red supergiant stage. Some may explode earlier in their evolution. Meanwhile, some massive stars lose most or all of their hydrogen before exploding. Such stars, often Wolf-Rayet stars, give rise to Type Ib or Type Ith supernovae. These explosions lack the signature hydrogen plateau, since the star's outer layers were gone. Instead, their light curves often decline more quickly and are powered largely by the radioactive decay of nickel, D6 to cobalt, 56 to iron, D6 in the ejector. By studying these differences, astronomers piece together the life histories of the progenitor stars. A Type Ice supernova with broad spectral lines might indicate an especially massive star that was stripped and possibly involved in a binary merger or had extremely powerful stellar winds. A Type 2 with a very long plateau might imply an especially extended red supergiant. Each dying star carries the imprint of its life into its death, visible in the explosion's properties. While we have focused on the dramatic, successful explosions, nature sometimes chooses a more silent finale. In recent years, evidence has emerged that some massive stars fail to go supernova at all, at least not in any luminous way. Instead, they collapse directly into a black hole, disappearing from view with barely a fuss. How would we notice such an event? Imagine a star that brightens a bit, perhaps as its outer layers respond to the initial core collapse, and then fades to nothing, no ensuing explosion. This appears to have been observed in a galaxy about 22 million light-years away, where a star of around 25 solar masses brightened modestly and then vanished, leaving no supernova. It seems that the star's core collapsed, but the shock did not blow the star apart. Instead, nearly the entire star just fell inward, swallowing itself into a new black hole. This phenomenon has been dubbed a failed supernova. It's essentially a collapse without an explosion. Gravity wins completely, and almost all of the star's mass slides past the event horizon of the nascent black hole. Only a feeble burp of energy might escape to tell the tale. For the galaxy at large, the star just quietly winks out. For the star itself, of course, it is a tremendous end. 98% of its mass collapsing into the black hole, maybe 2% getting flung out in that brief flare as the rest slurps away. Failed supernovae are a stark reminder that not all stellar deaths are flamboyant. Sometimes the star falls silent, leaving a dark remnant with no fireworks. These events are harder to find, but ongoing monitoring projects are trying to identify more of them by looking for massive stars present in old images that have since disappeared without a trace. If higher, mass red supergiants tend to die this way, it could explain why we don't see supernova progenitors above a certain mass. They might simply collapse directly and give no bright supernova, solving a little mystery about the apparent upper mass limit of supernova progenitors. Whether a star dies with a spectacular bang or a quiet collapse, the end result is a compact object and an ejection of material. These remnants then influence their surroundings for a long time. A young pulsar left from a supernova spins inside its nebula, energizing it with winds and radiation. A newborn black hole might produce relativistic jets, or it might just quietly accrete any remaining fall, back material from the collapse. The ejecta from a successful supernova expand and eventually mix into the galaxy's gas. Multiple supernovae in a star, forming region, such as those in a cluster of massive stars, can create superbubbles, huge cavities in the interstellar medium, swept clear by consecutive blasts. In starburst galaxies, where many massive stars die in a relatively short span, the combined effect of many supernovae can drive galactic winds. Enormous outflows of hot gas blowing out of the galaxy's disk into intergalactic space. These winds carry metals out of the galaxy, dispersing the products of star formation far and wide. Thus, supernovae not only shape where new stars form locally, but also how galaxies evolve globally by regulating gas flows. It's thought that without supernova-driven winds, galaxies might contain much more gas and form stars too efficiently early on, whereas with winds, some gas is ejected and star formation is extended over billions of years. Our own Milky Way has fountains of gas likely powered by past supernovae clustered in regions like the galactic center. We even detect cosmic rays, high-speed particles, that originate from the shock waves of long-ago supernovae, still diffusing through space and occasionally hitting Earth's atmosphere. These cosmic rays are a byproduct of supernova remnants. As their shocks propagate, they act like giant accelerators. Particles bounce back and forth across the shock front, gaining energy with each crossing, until some are flung out at near light speed. The Milky Way is filled with these relativistic particles, and about 90% of the cosmic rays that strike us are protons, thought to be accelerated by supernova shockwaves. Supernovae, then, are also cosmic ray factories, shooting out subatomic bullets that zip through the galaxy. Some of those particles may even have affected Earth's biology over the eons by contributing to background radiation or seeding cloud formation. In any case, they are yet another thread of connection between stellar deaths and our own world. On Earth, we have literally found the fingerprints of nearby supernovae in geological records. Deep sea deposits and lunar soil samples contain trace amounts of rare isotopes like iron, that are not produced in significant quantities by typical earthly processes. The most plausible source is a supernova that occurred a few million years ago near our solar system, dusting us with a thin coat of radioactive ash. Indeed, layers of extraterrestrial iron sounded have been detected in ocean crusts, corresponding to around 2003 million years ago, and even in Antarctic snow from recent times. This is tangible evidence that a supernova occurred in our cosmic neighborhood in the relatively recent geological past. Fortunately, it was not so near as to cause a mass extinction, but near enough to sprinkle Earth with a detectable layer of star stuff. Perhaps such events even had subtle effects on our planet. Some have speculated about minor climate impacts or changes in cosmic ray flux affecting cloud cover. In any case, it's awe inspiring to realize that Earth has been showered by the debris of explosions that happened far away. We walk amid atoms that fell from the skies of long-gone stars. The very iron in your blood could include atoms flung out by a supernova that occurred before humans walked the Earth. Across cultures and centuries, humans who witnessed supernovae have been mesmerized and mystified. The sudden appearance of a new star, where none had been seen, often regarded as an omen or a divine signal. Ancient Chinese astronomers meticulously recorded these guest stars and noted their brightness and duration. In 1006 AD, a supernova in our galaxy was recorded as a star bright enough to read by at night. In 1054, the supernova that created the Crab Nebula was observed by Chinese, Japanese, and possibly Native American skywatchers, who saw a star rivaling the moon's brightness for weeks. In Europe, the notion of an unchanging heaven was challenged in 1572, when Tycho Brahe observed a brilliant new star. It helped upend old models of the cosmos. These events entered law and record. They were variously interpreted as heralds of great change, the births of new celestial beings, or the wrath of gods. One can imagine ancient peoples gazing up in wonder and fear at a glowing orb that hadn't been there before, not knowing they were witnessing the death of a distant sun. They lacked our scientific understanding, but they felt the grandeur of the event. They called them new stars, not realizing they were actually witnessing a star's death, or more poetically, its transfiguration. In a way, the ancients were right to be awed. These guest stars were harbingers, though not of human affairs, but of cosmic renewal. They heralded the dispersal of elements that would one day form new stars, new planets, perhaps new living beings. Today, with knowledge in hand, our awe has only deepened. We no longer see supernovae as unpredictable omens. We see them as essential processes in the universe. They are the engines of cosmic evolution, the means by which simple matter is churned into complexity and spread throughout galaxies. They are at once destructive, obliterating a star, potentially sterilizing nearby planets, and creative, sowing the seeds of creation far and wide. In their violence, there is profound generosity. The star gives all it has to the cosmos in its final moment. The gas and dust rushing outwards will, in time, collect into new clouds, igniting new stars with planets around them. Perhaps on those planets, new life will one day spring forth, built from the atoms of that long, dead star. This cycle links us to the stars in an intimate way. Look at the gold of a ring on your finger. Those gold atoms likely formed in either a supernova or a neutron star merger eons ago. The calcium in your teeth was flung out by an exploding star before the sun was born. When you gaze at the night sky, you are literally seeing ancestors of your own flesh and blood. Philosophers and poets have long noted the connection between death and rebirth. In mythology, the phoenix is a creature that bursts into flame, and from its ashes, a new phoenix rises. The universe offers its own phoenix tale. A star dies in fire, and from its ashes, new stars arise. Every supernova is a phoenix event on a grand scale. The ashes do not remain cold and dead. They eventually become the building blocks for new astral flames. The cosmic dust from supernovae drifts through space for ages, but given the tug of gravity and the shelter of a molecular cloud, it can coalesce again. Our solar system is one such recoalescence, a mix of gas and supernova dust that assembled into a star, planets, and on one of those planets, creatures who can ponder the process. It is a humbling and inspiring realization. The universe recycles. Stars sacrifice themselves so that the cosmos can be ever more enriched and complex. In a poetic sense, the stars die so that we might live. As we conclude this journey through the death of stars, we stand in awe of the grand narrative it presents. A supernova is not an isolated incident. It is a chapter in the cosmic story. It's the dramatic climax in the life of a massive star, but also the prologue for the matter that star releases. From the soundless flash that announces a star's demise to the glittering nebula that remains and the new stars that will be born from it, the supernova story is a saga of transformation. It reminds us that even in destruction, there is profound creativity. The universe takes the incandescent bow of a star and uses it to sow gardens of new suns. The next time you look up at the night sky, consider that somewhere out there, at this very moment, a star is meeting its spectacular end. You will not hear it, but if the star is close enough and your timing fortunate, you might one night see a new point of light. A silent shout across space, the death cry of a star that lived perhaps millions of years. And though it died alone in the vacuum, its effects will not be lonely. The elements it scatters will mingle and dance in nebulae. Some will become parts of new living beings who may one day also look up and wonder. In the grand scheme, the death of stars is as necessary as their birth. From cosmology's perspective, stars must die for galaxies to thrive and for life to exist. Our world is the way it is because countless stars died in the Milky Way before the sun even ignited. There is an emotional power to this knowledge. We see in the supernova a reflection of a natural truth, that endings feed beginnings, that great beauty can arise from great upheaval. The supernova is violent, yes, a masterpiece of cosmic violence, but it is also the universe's most brilliant creative act, forging heavy atoms and casting them forth to enable planets and life. It is the universe writing poetry with fire, a verse about impermanence, transformation, and interconnection. The star which lived in solitude ends by giving itself to everything. Its light races across the cosmos. Its shrapnel becomes the stuff of new worlds. In contemplating the death of stars, a supernova story, we find ourselves filled not with despair, but with a profound sense of connection and renewal. The atoms in our bodies were born in stellar furnaces and scattered by supernova, binding us to those majestic events. When we marvel at a supernova through a telescope, we are in a way beholding our own origins. The cosmos is not